Good evening everyone. Good evening. I welcome you all again to the NEET Elite. Hope all of you are doing great, having the good time at home. Well, people, if I'm audible and visible to everyone, do let me know in the chat box. Do let me know in the chat box if I'm audible and visible to everyone. Good evening, guys. Good evening. Welcome to the session. Welcome to the one-shot series, guys. Welcome to the one-shot series. Yes. Wonderful, guys. Hi, Kavya. Hi, Kirti. Hi, Danya. Hello, Jaya. Hi Aryan, how are you guys doing? I cannot call all the names, guys. The list is too long. Yes, I must say that. Yes. Hi Khushi. Hello Ayat. Hi Nayana. Nayana, हम Sunday को भी class रखते हैं. Sunday को we do the one-shot series, as you all must be knowing. Yes. So people, let me know before starting the session if you guys are super duper excited for this session. As you all must be knowing, today we are going to start and finish the redox reactions. Yes. Yes, so you have to stay with me till 12. Are you guys ready for that? Are you guys ready for that? Yes. Yes, Adnan, I'll be starting atomic structure soon. Just wait for it. Yes. Wonderful, guys. Great. Okay, so before starting the session, let me introduce myself. As you all must be knowing now, my name is Wasim Bhatt and I'm your chemistry master teacher right here. Okay, so people, for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Which I always say in every session, okay? Alright, so talking about the Vedantu NEET Pro subscription, first of all, if you guys are getting enrolled in this, what all benefits you guys are going to get? Let me tell you guys, if you are getting enrolled in the Pro subscription, you guys are going to get 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5 plus years of experience who will be training you personally for the upcoming NEET 2021 as well as 2022. And at the same time, you have got the option to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu right here through this Pro subscription, right? And people, at the same time, we are going to cover everything in this, which includes your micro as well as crash course right here, okay? And for the ones who are going to write your NEET in 2022, we have come up with 4 different plans, as you all can see, and the best offer right here which you can have, that is the 50% off. On every plan right here, you have got 50% off. Yes, people, the 1-month plan, 3-month plan, 6-month plan, and 12-month plan, after the 50% off, you guys are just getting it for 2.5K, 6.75, 14K, and 32K respectively. And let me tell you, this deal is valid just between 14th till 17th September. Yes. Okay, so people, how to get enrolled in it, how to get this Pro subscription, let me tell you, there's a link in the description box of the video. I want you guys to click on that link, use the coupon code as WSPRO. On using this coupon code of WSPRO, you guys are going to get 50% off right here if you're enrolling yourself during this phase, 14th to 17th, yeah? Okay. So let me know in the chat box first if you are super duper excited for the redox reactions. Yes. Let's try to shoot the bullseye, guys. Yes, you can see over here. Let's try to shoot the bullseye. Let's start it and finish it. Let's kill all the concepts in the redox reactions. Are you guys super duper excited for it? Let me know in the chat box. Give me the thumbs ups. Yes. Let me see the josh of the session first. Let me see the josh of the session. Let me see the josh of the session. Yes. Sania, I'm all great. Walaikum Assalam. मैं बिल्कुल बढ़िया हूँ. आप बताओ. Yes, Mohammed Yawar, everything will be covered here. Everything will be covered here. Yes. Exactly. So let's get started with something called as redox reactions. And the first thing which I'll be discussing right here, I'll be exactly starting from the basics, guys, as if you have never started redox, okay? I'll be exactly starting redox reactions and I'll be finishing it up in the tonight's session only, yeah? Yes. Okay, so let's get started with something called as oxidation state, which is the first thing which we are going to discuss right here. What do we mean by the term oxidation state? Okay, as you all can see the definition, it is defined as the charge present, which can be a real or virtual on an atom, on an element in a given compound. See guys, what is this oxidation state as per its definition? Oxidation state is the charge present on the element, or the charge which appears to be present on the element, right? It is the charge present on the element or the charge which appears to be present on the element in a given compound. Yes. Now the point is, what is meant by that? What is meant by that? Yeah. Let's get to know that in detail. Just a second, guys. Yeah. Let's get to know the term oxidation state first. See guys, first of all, as you all must be knowing, broadly classifying, we have got two types of compounds. One you call as ionic compounds, another one you called as covalent compounds. Yes, broadly speaking, we classify compounds into two different forms. One is called as ionic, one is called as covalent. Yes, ionic compounds are the ones in which ionic bond will be present, and covalent compounds are the ones in which covalent bond will be present, broadly speaking. Yes. Now guys, if I take one common ionic compound, for example, NaCl. Let's say this is one common ionic compound which I am taking, NaCl. At the same time, let me take one common covalent compound, that is H2O, water, or let me take NH3, okay? All right. So first of all, let's get to know about this ionic compound NaCl right here, okay? See guys, the charge present on the element in a given compound is what I call as oxidation state, or the charge which appears to be present on the element in a given compound is what we call as oxidation state. What do we mean by that? Understand guys, if I talk about this NaCl right here, this NaCl is made up of two things. One is your sodium, one is chlorine. Yes, and as you all must be knowing, sodium, it is a typical metal and chlorine is the non-metal. And as per the property of metals, they have got tendency to lose the electrons. And what about the property of the non-metals? They have got tendency to gain the electrons. Yes. So how this NaCl would have got formed? Let's talk about that first. How this NaCl would have got formed right here. Let me tell you guys, this sodium, it would have lost one electron and it would have got converted into Na positive. Yes. And the electron which would have been given by this sodium, this same electron would have been accepted by this chlorine, and this chlorine, after accepting the electron, it would have got converted into Cl negative. Yes. So people, I got something called as cation right here, I got something called as anion right here. Since both the ones have got equal and opposite charges, the cation and anion which got formed right here, both the ones have got equal and opposite charges. Can I say there will be electrostatic force of attraction between this cation and this anion? And let me tell you first of all, this electrostatic force of attraction between this cation and anion is what I'll be calling as the ionic bond. Yes. Alright, now people, as you all can see, if I ask you what is the charge present on this sodium right here, what is the charge present on this chlorine right here, you will say simply sodium over here is present in the form of Na positive and chlorine right here is present in the form of Cl negative. So can I say there is 1 unit of positive charge on sodium? Can I say there is 1 unit of negative charge on this sodium, on this chlorine right here? So I can simply say this plus 1 is the oxidation state of sodium right here in NaCl, and chlorine, this chlorine, it is present in, it has got -1 charge. I'll say -1 is the oxidation state of chlorine right here in this compound. And as we all know, the charge present on the element in a given compound is what we call as oxidation state. So I must say the oxidation state of sodium right here is +1 and the oxidation state of chlorine right here is -1. Okay. And the people at the same time, if you would have noticed one thing, I can say in this ionic compound, there was the complete transfer of electrons. Yes, there was complete transfer of 1 electron, as I can say over here. What is that? See, sodium has given 1 electron and chlorine has accepted the same electron. So sodium has lost 1 electron completely and chlorine has gained 1 electron completely, right? So in case of ionic bond, I can first of all say there is complete transfer of electrons. Yes, and if there is complete transfer of electrons, I can simply say the charges present on these atoms right here, these are the real charges. These are not the virtual charges. Yes, because right here there was the complete transfer of electrons, and as we know, due to the complete transfer of electrons, what happens? There will be real charges present on these atoms right here. So I want you guys to remember one thing: in case of ionic compounds, the charges present on the atoms are the real charges. Yes, these are the actual charges, real charges. Okay, in case of what? In case of ionic compounds. Okay. Now people, at the same time, in case of covalent compounds, what happens? First of all, in case of covalent compounds, there will be what? There will be what? Sharing of electrons, as you all can see in case of water. Okay, if I take the structure of water right here, first of all, this is the structure of water. Okay, Now people, if I talk about this bond pair between oxygen and hydrogen, I was expecting this bond pair to be present at the center. Yes, because this is the covalent bond between oxygen and hydrogen, and covalent bond is formed by the mutual sharing of electrons. So I was expecting this bond pair of electron to be exactly present at the center. But as you all must be knowing, in your periodic table, fluorine is the maximum electronegative element, followed by oxygen, followed by nitrogen. Yes, so due to the electronegativity difference between oxygen and hydrogen, I must say this bond pair will get slightly shifted towards oxygen, by means of which the electron density on this oxygen, it will get increased, and that increase in the electron density of the oxygen around it, that I'll be representing by minus delta. At the same time over here, I'll be representing it by plus delta, right? Very simple concept, guys. I was expecting the electron pair, I was expecting the bonded pair of electron to be present at the center, but as we know, oxygen is more electronegative. If oxygen is more electronegative, it has got more tendency to attract the bonded pair of electron towards itself. That is why this electron pair will get slightly shifted towards oxygen, due to which there will be slight negative charge and slight positive charge on oxygen and hydrogen respectively. Yes. At the same time, if I consider this bond between oxygen and hydrogen, again oxygen is more electronegative. So the bonded pair of electron between oxygen and hydrogen, that will be slightly shifted towards oxygen, by means of which oxygen will again get slight negative charge. At the same time, hydrogen will again get slight positive charge. Very simple. Correct? So people, if I ask you, are these the actual charges present on the atoms? These would have been the actual charges if there would have been the complete transfer of electrons. But right here, there is no transfer of electrons. There is just the shift of bonded pair of electrons. Yes, there is no transfer of electrons. There is no complete transfer of electrons, I must say, in case of your covalent compounds. So the charges present on these atoms, these won't be the real charges. These are going to be the virtual charges right here. These are the charges which are not actual. These are the charges which appear to be present on the atoms. Okay, and the charges which appears to be present on the atom in a compound is also what we call as oxidation state. So I must say the oxidation state of hydrogen right here is +1. I must say the oxidation state of hydrogen right here is +1, and oxidation state of oxygen right here is -2. Yes, but at the same time, you should remember, these are not the actual charges present on these elements right here. These are not the real charges, okay? These are the charges which appear to be present on the atoms due to the electronegativity difference between them, yeah? Very simple, okay? So people, remember, at the same time, in case of covalent compounds, the charges are virtual, okay? These are not the real charges. These are not the actual charges. These are the charges which seems to be present on the atoms due to the electronegativity difference. Very simple, okay? Yes. Similarly, if I talk about NH3, as you all must be knowing, the structure of NH3, it is something like this. Yes, the structure of NH3, guys, okay? If I consider this bond between nitrogen and hydrogen, I would say this bond is formed by one electron pair. One electron was given by nitrogen and one electron was given by hydrogen. So again, I was expecting this covalent bonded pair to be exactly present at the center, but it will be slightly shifted towards nitrogen because nitrogen is more electronegative. As a result, nitrogen will get slight negative charge due to the shift of this bond pair. At the same time, hydrogen will get slight positive charge on it, right? At the same time, if I talk about this single bond between nitrogen and hydrogen, again nitrogen is more electronegative. So this bonded pair of electron which I was expecting to be present at the center, this will be again slightly shifted towards nitrogen, by means of which nitrogen will get slight negative, hydrogen will get slight positive. At the same time, due to this shift of bond pair towards nitrogen, again nitrogen is getting minus negative charge and this is getting slight positive charge. Yes. So people, are these actual charges present on these atoms right here? These are not the actual charges. These are the charges which appear to be present on the atom, which appears to be present on the element in a given compound. Yes, and the charges which appears to be present on the given compound, we call that as the oxidation state. Yes. Guys, I have taught the titration. Just go through the playlist of the Redox. I have taught that. Equivalent concept, वही तो titration होता है. Okay, so people, if I ask you what is the charge which seems to be present on this nitrogen, it's going to be -3. So I'll be calling this -3 as the oxidation state of nitrogen right here. What is the charge which seems to be present on this hydrogen right here? It's +1. So +1 is the oxidation state of this hydrogen. Similarly, +1 is the oxidation state of this hydrogen. And at the same time, +1 is the oxidation state of this hydrogen at the same time. Yeah. So I'm sure you got few things right here. What is that? Number one, oxidation state is the charge present on the atom It is a charge which is present on the element, or the charge which appears to be present on the element in a given molecule. We call that as the oxidation state, yeah? Okay, and in case of ionic compounds, the charges are real. In case of covalent compounds, the charges are virtual. Yes, this is something which I want you guys to remember right here. Okay, now guys, have a look. For ionic compounds, the charges are real, as I told you, and for covalent compounds, the charges are virtual, as you all must be knowing now. Okay, now guys, let's get to know the rules. Let's get to know how this oxidation state on an element can be calculated. Okay, there are few rules which you need to remember right here in order to calculate the oxidation states of different elements in a compound. Yes, and I want you guys to remember those rules. Okay, and people, at the same time, you'll be getting the PDF of this session through the Telegram after the session, right? You'll be getting the PDF also. Okay, so you do not need to worry about it. Right? So let's get to know the rules by means of which we can calculate the oxidation state of an element in a given compound. Now guys, understand guys. See, the first rule, which is written right here, the oxidation state of an element in its standard state is taken as 0. The term comes over here, the standard state. What is standard state? Yes? Understand guys. Standard state, or we call it as the elemental state. We call it as the elemental state. Or at the same time, we can call it as the native state as well, right? We can call it as the native state as well. Let me tell you guys, the standard state of the element is that state in which the element exists in the nature. Yes, that state in which the element exists in nature, that's what we call as the standard state. For example, as you all must be knowing, oxygen in nature exists in the form of O2 gas. Nitrogen in nature exists in the form of N2 gas. Similarly, fluorine in nature exists in the form of F2 gas. Bromine in nature exists in the form of Br2 liquid. Iron in nature exists in atomic form. Zinc in nature exists in atomic form at the same time. Yes, so I'll be calling these are the standard states of these elements. Yes, or we call these as elemental states or native state. It's your wish, whatever you want to call them. Yes, and remember, whenever the element is present in its standard state or native state, at that time its oxidation state is taken as 0. So I must say the oxidation state of oxygen right here is 0, nitrogen is 0, fluorine is 0, bromine is 0, iron is 0, zinc is 0. Yes, so remember, whenever the element will be present in its standard state or native state or elemental state, its oxidation state must be taken as 0, right? Number 1. Number 2 guys, see, if I talk about the group first elements, which are what we call as alkali metals. Yes, your group first elements, these are what we call as alkali metals, and group second elements, as you all must be knowing, these are what we call as alkaline earth metals. Yes. Now guys, if I talk about these group first elements, they have got only one electron in their outermost shell. So is it easy for them to lose this one electron, or they will be gaining 7 electrons? I say they can easily lose 1 electron to get the stable state, to get the stable electronic configuration. After losing the electron, all these group first elements, they get plus 1 unit of charge on them. They get 1 unit of positive charge on them after losing the electron. So remember, all your alkali metals, all your group first elements, they'll be showing the plus 1 oxidation state always right here. Yes? 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 Yes, Harim, titration will be also done. Just wait for it. Titration, everything will be done. Just wait for it. Wait for it. Yeah. Okay. Now, similarly, guys, talking about the group second elements, which is what we call as alkaline earth metals. And as you all must be knowing, they have got 2 electrons in the outermost shell. Now, people, if I ask you, is it easy for them to lose these 2 electrons or they can gain 6 electrons? What is easy for them? The easy thing that they can do right here is to lose 2 electrons, and if they lose 2 electrons, I'll say they can show the plus 2 oxidation state right here. So remember, group first elements, they'll be always showing plus 1, and group second elements, they'll be always showing plus 2 oxidation state right here. Okay, very, very, very simple. This is one more rule which you guys are supposed to remember right here. Okay. Now guys, talking about one more rule, what is that? The oxidation state of hydrogen is generally taken as plus 1 when attached to more electronegative element. As you can see in these examples, hydrogen is everywhere attached to more electronegative element. And remember, whenever hydrogen will be attached to the more electronegative element, hydrogen is going to have plus 1 oxidation state always. Yes, whenever hydrogen will be attached to the more electronegative element, at that time hydrogen shows the plus 1 oxidation state right here. Okay, Remember this. Yes, Varuni, I'll be teaching inorganic at the same time. Just wait. All right. Now, people, talking about the same hydrogen when it is attached to the less electronegative element. Yes, whenever hydrogen will be attached to the less electronegative element than itself, okay, its oxidation state will be taken as -1. Its oxidation state will be taken as -1. Over here, as you all can see in these examples, hydrogen in both the examples is attached to less electronegative element than itself, or I can say it in like this. I can say the electronegativity of hydrogen is more than that of sodium, and at the same time electronegativity of hydrogen is more than that of magnesium. And remember, whenever hydrogen will be attached to more electronegative element than itself, its oxidation state will be taken as -1 at that time. Yes, so I'll say the oxidation state of hydrogen in both the cases right here will be -1. Correct? Now guys, let's move on to one more rule, which is regarding the oxygen. And as you all must be knowing, the oxidation state of oxygen, it is generally taken as -2 when attached to less electronegative element than itself. For example, you have got all these cases where oxygen is attached to less electronegative element than itself. Yes. Okay, so whenever you see oxygen attached to less electronegative element than itself, its oxidation state will be taken as -2, except in few compounds, which I'll be telling you in a while. Yes, so remember, over here oxygen is going to show -2 oxidation state, right here also -2, right here also 2. Yes. So remember, whenever oxygen will be attached to the less electronegative element than itself, its oxidation state you guys are going to take as -2 generally, except in few compounds, which I'll be telling you in a while. Yeah. Now guys, one more thing for peroxides. First of all, what are peroxides? Whenever you see a single bonded linkage between oxygen and oxygen, whenever you see a single bonded linkage between oxygen and oxygen, this single bonded linkage I'll be calling as the peroxide linkage. Yes, this single bonded linkage I'll be calling as the peroxide linkage, and the compound in which peroxide linkage exists, that compound I'll be calling as the peroxide. Yes, and whenever oxygen shows the peroxide linkage, oxidation state of oxygen is either going to be -1 or +1. When it's going to be -1, when +1, you'll be getting the idea in some time. Okay, first thing, very simple idea I'm giving you. Whenever you see a single bonded linkage between oxygen and oxygen, I call this single bonded linkage as the peroxide linkage. And whenever there is going to be the peroxide linkage between oxygen and oxygen, the oxidation state of oxygen is either going to be -1 or +1. Yes. Now what are its examples? If I talk about the hydrogen peroxide, just give me a second. If I talk about the hydrogen peroxide, as you all must be remembering its structure. Yes, this is the structure of hydrogen peroxide, as you all must be knowing. Now guys, understand few important things which I'll be sharing right here with you. Okay, for example, I have got a single bond between A and B. Let's say I've got a single bond between A and B, and over here I've got, for example, double bond between A and B, and over here I've got a triple bond between A and B right here. And I'm assuming the electronegativity of B over here is greater than the electronegativity of A. So I can say this bonded pair of electron, this will be shifted towards B, by means of which B would have got minus delta charge and A would have got plus delta charge. So I must say the oxidation state of B right here is -1, oxidation state of A right here will be +1. Similarly, over here we have got a double bond, right? We have got a double bond, and B is more electronegative. Can I say on B there'll be -2 charge? I'll be saying now, I won't be writing minus delta, I'll be directly saying -2, and over here on A there'll be +2 charge. And similarly, there's a triple bond between A and B, so I would say all the three bonded pair of electrons right here, they'll be shifted towards B, so B will be getting -3 charge, A will be getting +3 charge right here. Okay, now guys, if I talk about the structure of hydrogen peroxide right here, first of all, if I consider this single bond between oxygen and hydrogen, if I ask you which one is more electronegative among these two, you'll simply say oxygen is more electronegative. If oxygen is more electronegative, I would say the electron pair which I was expecting to be at the center, it will be slightly shifted towards oxygen, by means of which oxygen will get -1, hydrogen will get +1. I'm not going to represent the charges by delta and all now. I'm directly going to say -1 +1, -2 +2, and so on. Yes. Now people, at the same time, if I consider this single single bond between oxygen and oxygen. People, on one side we have got oxygen, on another side we have got oxygen. So the tendency with which this oxygen will be attracting this bonded pair of electron towards itself, with the same tendency the other oxygen atom is going to attract this bonded pair. So I would say this bonded pair of electron will be exactly present at the center. So there will be no contribution of charge by this bonded pair of electron on this oxygen or on this oxygen. Yes, so this bonded pair of electron is exactly going to be at the center. If it is exactly going to be at the center, I would say its contribution towards the charge on this oxygen or on this oxygen is going to be nothing, right here. Yes, and people, if I talk about this single bond, oxygen is again more electronegative. So oxygen has got more tendency to attract this bonded pair of electron towards itself, by means of which oxygen will get -1 charge, hydrogen will get +1 charge. So I must say the oxidation state of oxygen right here is -1, and over here again it is -1. Yes, so remember, whenever oxygen shows the peroxide linkage, at that time its oxidation state is going to be -1 or +1, which I'll be showing you in some time, right? Remember that, correct? Okay, now people, there are certain compounds called as superoxides, as you all must be knowing. Whenever you see oxygen in the form of O2 negative, for example, if you take the case of potassium peroxide, sodium peroxide, rubidium superoxide, if I take the case of potassium superoxide, rubidium superoxide, okay, any superoxide, whenever you see the oxygen present in the form of O2 negative, we call it as the superoxide. And remember guys, whenever we talk about oxidation state is defined per atom. It is defined for a single atom. Now guys, understand one important thing right here. Can I say on two oxygen atoms right here there is -1 charge? If there is -1 charge on two oxygen atoms, so on one oxygen atom, what will be the amount of charge? Charge is going to be -1/2, and the charge present on the atom in a given compound, that's what we call as oxidation state. So I can say whenever oxygen will be present in the form of O2 negative, the charge present on one oxygen is going to be -1/2, or I can say the oxidation state of oxygen in case of superoxides, it's going to be -1/2 right here. Yes? Okay. Let's move on guys, let's move on to few more compounds which are what we call as oxyfluorides, and the examples of these oxyfluorides are OF2 and O2F2, okay? And people, let me tell you, these are the only compounds in which the oxygen shows the positive oxidation state. These are the only compounds in which the oxygen shows the positive oxidation state. And how they show the positive oxidation state right here? For that, you should know the structure of OF2 and O2F2, yes? And if I talk about the structure of OF2, as you all must be knowing, this is the structure of OF2. Yes, this is the structure of OF2. Now guys, let's get to know something interesting right here. If I consider this single bond between oxygen and fluorine, I must say fluorine is more electronegative than oxygen. So fluorine has got more tendency to attract the bonded pair of electron towards itself, by means of which fluorine will get minus charge. At the same time, oxygen will get +1 charge. I'm not going to represent it by delta or something. Yes, I'm directly going to write the charges -1 +1. Yeah. At the same time guys, if I talk about this single bond between oxygen and fluorine, again you can say fluorine is more electronegative, by means of which fluorine will get -1 charge, oxygen will get +1 charge. If I ask you what is the net charge present on this oxygen right here, you will say +2. So I must say the oxidation state of oxygen in case of OF2, it is +2 simply. Yeah. Now guys, at the same time, if I talk about O2F2, this is the structure of O2F2 right here. This is the structure of O2F2 right here. People, is there a single bonded linkage between oxygen and oxygen? Absolutely, there is a single bonded linkage between oxygen and oxygen. And the single bonded linkage between oxygen and oxygen, this is what we call as peroxide linkage. And as I told you earlier, in case of peroxide linkage, the oxidation state of oxygen can either be -1 or +1. Right here, it's going to be +1. And how come it's going to be +1? Understand that as well. People, if I consider this single bond between oxygen and fluorine, I must say fluorine is more electronegative, by means of which fluorine will get -1 charge, and at the same time, due to this bond, oxygen is going to get +1 charge. Very, very, very simple. Now guys, if I consider this peroxide linkage, I will say the electron pair will be exactly present at the center, because on one side there is oxygen, on another side there is oxygen. The tendency with which this oxygen is going to attract this bonded pair of electron towards itself, the same tendency will be for this oxygen to attract the same bonded pair of electron towards itself. So I must say there is no contribution of the charge, there is no contribution of this peroxide linkage on the charge present on this oxygen or this oxygen. Yes, very simple. Okay. Now people, if I consider this single bond between oxygen and fluorine, again I can say fluorine is more electronegative. If fluorine is more electronegative, so I will say fluorine will simply say -1. This is going to have +1. So the charge present on this oxygen is +1. The charge present on this oxygen is +1. So the oxidation state of oxygen right here in case of O2, F2, it's going to be what? It is going to be +1, as you all saw right here. Yes? People, let me know in the chat box if everything is clear till here or not. Till then I can have some water. Yes? 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 Someone is asking, sir, please talk in Hindi. Bro, this is complete English channel, yeah? This is for the ones who cannot understand Hindi, okay? That's why I'm supposed to talk in English. Varna Hindi mein main padhata hu actually. Yes? Okay. Let's move on, guys. Let's move on, keep the josh high. Yes, the oxidation state of halogens is generally taken as -1 when attached to less electronegative element than itself. Yeah, as you all can see the examples. What are halogens? First of all, halogens are group 17 elements. Yes, fluorine, chlorine, bromine, iodine, astatine, these are what we call as halogens. Yes, and whenever halogen is going to be attached to the less electronegative element than itself, its oxidation state will be simply taken as -1. Yes. Very simple, yeah. As you all can see right here, this is the halogen attached to less electronegative element than chlorine. This is the halogen attached to less electronegative element than fluorine. This is the halogen attached to less electronegative element than bromine. So whenever halogen is attached to the less electronegative element than itself, its oxidation state will be simply taken as -1 right here. Yes? Okay. Now people, there are certain compounds in which the halogen shows the positive oxidation state at the same time. Yes. And what are those compounds? There are certain examples which I have given already on the screen. See guys, in case of Cl2O, in case of ClF3, in case of IF7, the halogen shows the positive oxidation state as well, right? Understand guys. If I talk about the structure of Cl2O, the rough structure of Cl2O, I'm making it like this. Yes. And people, if I'm considering this single bond, just give me a second guys. Let me change the color of the pen. Yeah. Okay. If I consider this single bond between chlorine and oxygen, I will say simply oxygen is more electronegative than chlorine. So oxygen has got more tendency to attract the bonded pair towards itself. So oxygen is going to have -1 charge. Chlorine is going to have +1 charge due to the shifting of the electron pair towards oxygen. Yes. Now guys, talking about this single bond, again the oxygen is more electronegative element, right, than chlorine. So oxygen will attract the bonded pair of electron towards itself, by means of which oxygen will get one more negative charge due to the shift of this electron pair towards oxygen, and at the same time chlorine will get +1 charge. Yes, so I can say the oxidation state of chlorine right here is +1, the oxidation state of chlorine right here is +1, the oxidation state of oxygen right here is -1. So this is the compound in which the halogen shows the positive oxidation state, OCl2. Simple, yeah. Similarly guys, if I talk about ClF3, as you all can see, this is ClF3, right? If I make its rough structure, it's going to be somewhat like this. Cl, this is F, this is F, this is F. So I will say due to this single bond, fluorine is more electronegative than chlorine. So fluorine will have -1, chlorine will have +1. Due to this single bond, fluorine -1, chlorine +1. Due to this single bond, fluorine -1, chlorine +1. Yes, what is the net charge on this chlorine right here? I'll simply say +3. So I'll say this is again one more compound in which the halogen is showing the positive oxidation state. Similarly guys, in case of IF7, IF5, iodine shows the oxidation state right here as +1, and in case of IF5, iodine shows the oxidation state +5. So people, in these compounds, the halogens show the positive oxidation state as well, and I want you guys to remember all these. Yes? Yes? Yes, Aksa, I have shown that oxygen shows -2 oxidation state. This is -1, -1, -1, kitna ho gaya? This is -2, right? Yes, this understood? Okay. Let's move on guys, let's move on. As you all must be knowing, fluorine is considered as the most electronegative element in the periodic table. So fluorine is the only element which always shows -1 oxidation state. Remember that guys. Fluorine is the most electronegative element. Its oxidation state will be always taken as -1. There is no other element in the periodic table which is more electronegative than fluorine. So remember. Fluorine always shows the oxidation state -1 right here. Yes? Okay. Now guys, talking about something called as the radicals. What are these radicals? First, remember this statement. Radicals are considered as the single unit and the charge present on them is taken as their oxidation state. Okay. What are radicals? Radicals are the atoms or the group of atoms having charge on them. Okay, any atom or group of atom having charge present on it, that's what I'll be calling as radical. For example, if I take the case of sodium, okay, if I keep +1 charge on it, if I take chlorine, I'm keeping -1 charge on it. For example, if I'm taking PO4, I'm taking -3 charge on it. So for example, if I talk about SO4, di-negative, similarly I talk N3, negative, something like this. Whenever you have the atom or group of atom having charge on it, that's what I'll be calling as the radical. And remember, radicals are considered as the single unit, and whatever is the charge present on the radical, that will be taken as its oxidation state. Yes, so people, this is the radical, this is the atom having charge on it. Whatever is the charge present on the radical, that's considered as its oxidation state. Whatever is the charge present on the radical, considered as its oxidation state. Whatever is the charge present on this PO4 right here, on this radical right here, it's going to be its oxidation state. Similarly, the oxidation state of sulfate right here is -2. Similarly, over here it's going to be -3. So radicals are first of all the atoms or group of atoms. Radicals are atoms or group of atoms which have got charge present on them, and these radicals are considered as the single unit, and whatever will be the charge present on them, that is going to be taken as its oxidation state. Very, very, very simple. Yeah. Okay. Let's move on and let's talk about few radicals. People, these are the radicals which we have, which you guys are supposed to remember. Oxygen having di-negative charge on it. Okay, I call this as oxide. N tri-negative, we call this as nitride. P tri-negative, we call this phosphide. S di-negative, we call this as sulfide. And since these are all the radicals, and whatever is the charge present on the radical, it's going to be taken its oxidation state. Very, very, very simple. Yes, very simple, guys, right? Okay. There are few more radicals which I want you guys to remember. All these are group of atoms having charge on them, and as I told you, radicals are considered as the single unit, and whatever is the charge present on the radical, that is going to be taken its oxidation state. So on this OH there is charge -1, so -1 is going to be the oxidation state of OH right here. Similarly, -1 is going to be the oxidation state on this CN right here. Similarly, -1 on this NC, on this SO4 -2, on this SO3 -2. So these are all the radicals. So whatever is the charge present on them, it's taken as their oxidation state, and these are the names of these radicals right here, which you must remember. Yes, yes, these are few more radicals, guys. PO4 tri-negative phosphate, PO3 phosphite, oxalate, thiosulfate, tetrathionate, and all these radicals, whatever is the charge present on them, that's going to be taken as its oxidation state. I'll be making you understand this in some time, right? Okay, now guys, these are few more radicals which we have. NH4 positive, NO positive, ammonium ion, nitrosyl ion. The charge present on the ammonium ion is +1, the charge present on nitrosyl ion is +1, and whatever is the charge present on them, that is taken as their oxidation state right here. Yes, okay. Now guys, one important thing. The sum of the oxidation states of all the elements present in a compound is always equal to the net charge present on it. What does that mean? Let's get in detail. Let's get started with something called as calculation of oxidation number of different compounds. Understand what I'll be doing right here. Okay, see guys. First of all, I'm given with a compound right here, and I want to calculate the oxidation state of chromium right here. Okay, understand what I'll be doing. Let's assume the oxidation state of chromium is X, but I've got two chromium atoms, it's going to be 2X then. The oxidation state of oxygen right here is -2. I have got 7 oxygen atoms, I'm multiplying it by 7. What is the net charge present on it? Net charge is -2, so I'm equating it to -2. I'll simply get the value of X right here as +6. So I'll say +6 is the oxidation state of chromium right here. Yes. Similarly, guys, if I talk about the oxidation state of sulfur right here, let's assume the oxidation state of sulfur is X. I've got 2 sulfur atoms, so it's going to be 2X. The oxidation state of oxygen is taken as -2. Yes, and there are 3 oxygen atoms. And what is the net charge present on it? Net charge is -2. Just calculate the value. You'll be getting the value of X right here as +2. Yes, you'll be getting the value of X right here as what? It's going to be +2. Yes. Similarly, if I talk about the oxidation state of nitrogen right here, you all can do it, correct? Let's assume the oxidation state of nitrogen is X, right? And hydrogen, when hydrogen is connected to more electronegative element, the oxidation state of hydrogen is taken as +1, which I told you a few minutes back. And how many hydrogen atoms do we have? 4 hydrogen atoms. What is the net charge present on it? Net charge is +1. So I must say the value of X right here is -3. And what was X? X was the oxidation state of nitrogen right here. Yes. Similarly, guys, if I talk about the oxidation state of chlorine right here, let's assume that to be X. The oxidation state of oxygen is going to be -2. How many oxygens do we have? 4 oxygens. And what is the net charge present over here? It is -1, right? So you'll get the value of X right here as +7. Okay, so chlorine right here is present in the +7 oxidation state. And at the same time, if I calculate the oxidation state of chromium right here, let's take the oxidation state of chromium as X. We have got oxygen right here. Its oxidation state is -2. How many oxygens do we have? 4 oxygens. What is the net charge present on it? It is -2. So you can get the value of X right here as +6. This is how we calculate the oxidation state of every element right here in different compounds. Yes? Yes? Well, Goyal, let me tell you, this is the English channel, so I'm supposed to talk in English only, bro. This is the English channel, okay? There are a lot of other Hindi channels created by Vedantu. You can watch the sessions from there as well, okay? This is the English channel, so I'm not supposed to talk in Hindi. I'm really sorry, bro. Yeah? Okay, let's move on. Let me give you a few more examples, guys. Let me give you a few more examples. Understand these examples as well, okay? These are important. These are important. See, guys. If I want to calculate the oxidation state of iron right here, I'll be assuming the oxidation state of iron as X, but I've got 2 iron atoms, so it's going to be 2X. The oxidation state of oxygen will be taken as -2, and we have got 3 oxygen atoms is equal the net charge present on it, which is 0. So I'll take the value of X right here as +3. So the oxidation state of iron right here in this compound will be simply +3. Yes. Similarly, guys, if I want to calculate the oxidation state of iron right here, let's take this as X. Let it be X right here. But right now we have got 3 iron atoms, so it's going to be 3X. The oxidation state of oxygen is going to be -2, and we have got 4 oxygen atoms, so I'm multiplying it by 4. The net charge present on this compound is 0. I'll get the value of X right here as +8 divided by 3. So +8 divided by 3 is the oxidation state of iron in case of Fe3O4. Yes? People, if I talk about the oxidation state of iron right here, as I told you a few minutes back, what is this Cn? This Cn exists in the form of Cn negative. It is a radical, and whatever is the charge present on the radical, that's taken its oxidation state, right? I told you this radical is considered as a single unit, and whatever is the charge present on this single unit, that's taken as its oxidation state, as you all must be knowing. Yes, let's assume the oxidation state of iron right here is X. On Cn, there is charge -1. How many Cn do we have? 6 Cn. What is the net charge? Net charge is -3. I can get the value of X as +3 right here. Similarly, guys, this is CO. This is CO. This is considered as the neutral. It is the neutral one. There is no charge present on it. Yes. Actually, in coordination chemistry, we call it as the neutral ligand, right? In your class 12 coordination chemistry, this is considered as the neutral ligand. It has got no charge on it, so there'll be no charge present on nickel right here. Similarly, guys, you can calculate the oxidation state of sulfur right here. It's going to be simply +6. You can calculate it, right? +2 + X -8 is equal to 0. You can get the value of X right here as +6. Yeah, very simple. Right, guys? There are a few more compounds. NH4, NO2, and Ki3, okay? In this compound, I'm going to calculate the oxidation state of this nitrogen separately, oxidation state of this nitrogen separately. Let me tell you guys, this NH4NO2, it exists in the form of NH4 positive, NO2 negative. Yes, it exists in the form of NH4 positive, NO2 negative. Now let's get to know what is the oxidation state of nitrogen right here and what is the oxidation state of nitrogen right here, right? Let's assume the oxidation state of this nitrogen as X. Hydrogen will show +1 oxidation state, and how many hydrogens do we have? We have 4 hydrogens, and what is the net charge present on it? Net charge present on it is +1. So the value of X right here I'll be getting as -3. So -3 is the oxidation state of this nitrogen right here. And what about the oxidation state of this nitrogen? Again, let's assume it as X, right? Oxygen will be show -2 oxygen state, and how many oxygens do we have? 2 oxygens. There is -1 charge on it. So I say the value of X right here will come as +3. So +3 will be the oxidation state of this nitrogen right here. Yes. So people, on this nitrogen there is -3 oxygen state. On this nitrogen there is +3 oxidation state. Remember it. It's very simple. Yeah. Yes. Now guys, talking about Ki3. What is the oxidation state of iodine in Ki3? First of all, potassium belongs to what? Potassium belongs to group first elements, and group first show +1 oxygen state, right? Let's assume the oxidation state of iodine is X, but we have got 3 iodine. It's going to be 3X is equal to, what is the net charge present on it? It is 0. So the value of X will come as -1/3. So -1/3 is the oxidation state of iodine right here in this compound. Yes, people, with this With this, we calculate the oxidation states of different elements in a given compound. Yes? Now, people, there is something interesting which you need to know. There is something interesting which you need to know. What is that interesting thing right here? Before talking about that, let me have some water, yeah? People, is it clear till here? Is it clear till here? Let me know in the chat box. Do hit the like button if you got it. Yes? Yes, we'll be talking about bleaching powder at the same time. Just wait for it, guys. Don't jump, don't jump. I'll cover everything. At the end, if anything remains undiscussed, you let me know that in the chat box. But don't jump. Just wait for it. We are going to cover every single thing right here. Okay? हाँ, अजर balancing भी सिखा दूंगा यार. Wait तो करो. Yeah. Okay. Let's move on and let's talk about the oxidation states from structures. Okay. See guys, before talking about the structures of the compounds, let me write one important statement right here, okay? And I want you guys to take a note of it. Remember, the maximum oxidation state of an element in a compound can be +7. +7 is the maximum oxidation state which an element shows, right? But there is one exception over here. What is that? I'm writing except osmium in OSO4, where it is +8. Yes, the maximum oxidation state of an element in a given compound is +7, but there is one exception, that is osmium. In OSO4, it shows +8 oxidation state. And people, it has been observed iridium sometimes shows +9 oxidation state as well. Iridium sometimes shows +9 oxidation state as well. Okay, but remember, we don't have to talk about these two things right here. I'm talking in general. The oxidation state of an element can be +7, the maximum, right? Whenever you'll be using the formula and you'll be calculating the oxidation state of the element, if by chance it comes out to be greater than +7, you need to consult the structure of the compound at that time. Okay, let me tell you, sorry guys, I forgot to turn it on the silent mode. Yeah. Okay, let's move on. What I was talking right here, I told you, whenever you want to calculate the oxidation state of any element in a given compound, if by using formula it comes out to be greater than +7, at that time you should know the structure of the compound. Yeah, at that time you should know the structure of the compound. And I'm going to talk about certain structures which are really very important, which you must remember from now onwards. Okay, understand guys. The first important structure which I'm making right here, that is CrO5 structure. Okay, let me tell you, CrO5, it has got a butterfly structure. Okay, it has got a butterfly structure, and let me tell you, the color of CrO5 is deep blue. It is deep blue in color. Yes, and what is the structure of CrO5? As you all must be knowing now, it has got the butterfly structure. Its structure is somewhat like this. Yeah, okay, this is the structure of CrO5 right here. This is the structure of CrO5 right here, which I want you guys to take a note of. Yes? Understand, guys. Understand. Now, let's get to know the oxidation state of chromium right here through the structure. People, if you'll ignore the structure, if I want you guys to calculate the oxidation state of chromium by using formula, what you'll be doing? You'll be assuming the oxidation state of chromium as X. You'll be taking the oxidation state of oxygen as -2. Since we have got 5 oxygens, the net charge present on it is 0. So the value of X will be coming as +10. Is +10 oxidation state of an element possible? +10 is not possible at all. And I told you, whenever the oxidation state of the element comes out to be greater than +7, you need to consult the structure of that. So I've already made the structure of this right here. Yes? Yes, now guys understand. If I talk about this double bond between chromium and oxygen, since oxygen is more electronegative than chromium, so oxygen is going to attract the 2 bonded pair of electrons towards itself, by means of which oxygen will get -2 charge, chromium will get +2 charge. If I talk about this single bond, oxygen is more electronegative, it will attract this bonded pair of electron towards itself, so oxygen will get -1 charge, chromium will get +1. If I talk about this single bond, again oxygen will get -1, chromium will get +1. If I talk about this single bond, again oxygen -1, chromium +1. If I talk about this single bond, this is -1, this is +1. Now people, let's get to know the net oxidation state, the net charge present on this chromium right here. It's simply going to be +6. So remember, the oxidation state of chromium can never be +10. It's always going to be +6 right here. Yes? Very, very simple it is, okay? People, there are more structures which you need to remember, okay? There are more structures which you need to remember. The second structure which I'm talking about right here is the Carose acid, right? H2SO5. Now people, let me draw the structure of Carose acid as well. It's going to be S double bond O. Yes, it's going to be S double bond O, okay? Now people, there are how many hydrogens? There are 2 hydrogens. So I'm going to attach these 2 hydrogens first of all, like this, right? I'm going to attach these 2 hydrogens right here. This H2SO5. Just a second, guys. Let's keep the double bond right here. Let's keep one more double bond right here. Let's keep the oxygen. Let's keep the oxygen. Let's keep the hydrogen. It's going to be H2S 1, 2, 3, 4, 5. H2SO5. This is the structure of Carose acid, which I want you guys to remember from now onwards, okay? Now people, if I want you guys to calculate the oxidation state of sulfur right here, you can do it by means of the structure. Yes, if you remember its structure. Understand what I'll be doing right here. Understand what I'll be doing right here. First, I'll be considering this double bond between oxygen and sulfur, and I must say oxygen is more electronegative than sulfur, so oxygen will get -2 charge on it, sulfur will get +2 charge on it. If I talk about this double bond between sulfur and oxygen, again oxygen will get -2, sulfur will get +2. If I talk about this single bond, it's going to be -1, this is going to be +1. If I talk about this single bond, this is -1, this is +1. If I ask you what is the net charge present on this sulfur right here, you'll simply say +6. So +6 is the oxidation state of sulfur right here in case of Carose acid H2SO5. Remember it guys from now onwards, right? Let me move on to one more structure, which is what we call as Marshall's acid, People, you should remember its structure. It is S double bond O, this is double bond O, this is oxygen, this is oxygen, this is sulfur, double bonded oxygen, this is oxygen with hydrogen attached on this side, one more oxygen with hydrogen attached on this side as well. Now people, first thing, what I'll be doing, I need to calculate the oxidation state of this sulfur and this sulfur right here. People, I'll be considering the double bond between sulfur and oxygen, and let me tell you, oxygen is more electronegative than sulfur, so oxygen will have -2 charge, sulfur will have +2 charge. Yes. Now people, if I talk about this double bond, oxygen will have again -2, sulfur will have +2. If I talk about this single bond, oxygen will have -1, sulfur will have +1. If I talk about this single bond, oxygen -1, sulfur +1, because we know oxygen is more electronegative than sulfur. If I ask you what is the net charge present on this sulfur right here, you will say +2, +2, +1, +1, that means +6. And what about this sulfur? Again, this sulfur will have +6 by using the same technique by means of which we get the oxidation state. Yes, very, very simple thing it is. Remember, the oxidation state of sulfur in case of Carose acid, it's going to be +6. I'm moving on to one more structure, which is S4O6 dinegative. People, let me tell you the structure of S4O6 dinegative. It is S double bond O, this is double bond O, this is sulfur, this is sulfur, this is sulfur, this is double bond, this is double bond, oxygen having the negative charge on it, this is oxygen having the negative charge on it. This is the structure of S4O6 dinegative right here, okay? And if I want you guys to calculate the oxidation states of all the sulfur atoms right here, how will I be doing it? How will I be doing? The same thing which I'll be doing. First, let me consider this double bond. Oxygen is more electronegative, so oxygen will have -2, sulfur will have +2. If I talk about this double bond, oxygen -2, sulfur +2. If I talk about this single bond, oxygen again more electronegative, so -1, this is +1. So if I consider this single bond, on one side we have got sulfur, on another side we have got sulfur, so electron pair will be exactly at the center. If I consider this single bond, nothing will happen. On one side sulfur, on another side sulfur, electron pair exactly at the center. If I can't talk about this single bond, nothing will happen. Again, on both the sides we have got sulfur atoms. Yes, so charge on this sulfur is 0, charge on this sulfur is 0. What about the charge on this sulfur? Since due to this double bond, oxygen is more electronegative, so oxygen will have -2, sulfur will have +2. Due to this double bond, oxygen -2, sulfur +2. Due to this single bond, oxygen -1, sulfur +1. Let's calculate the oxidation states of different sulfur atoms right here. People, let me tell you the oxidation state of this sulfur is +5. What about this one? It is 0. What about this one? It is 0. What about this one? It is +5. So the correct set of the oxidation states of different sulfurs right here in case of S4O6 is going to be +5, 0, 0, +5. Yes? Okay. Yes, let me tell you in the chat. Let me know in the chat box, guys, if it's clear to everyone. Yes, travel expert will be doing the one-shot electrochemistry as well. Yes, yes, yes. Arjun, basically there was some connectivity issue yesterday, bro. That's why I couldn't attend the yesterday's session. Yeah, I couldn't take the yesterday's session. There were some connectivity issues. Yeah. Okay. Walaikum salam, Amir. Walaikum salam. I'm moving on, and let me give you a few more structures. There is something called as bleaching powder, CaOCl2. Let me talk about the structure of CaOCl2 as well. This is the structure of CaOCl2. Yes. Okay. Now guys, first thing, if I consider this single bond between chlorine and oxygen, let me tell you, oxygen is more electronegative than chlorine. So oxygen has got more tendency to attract the bonded pair towards itself. So oxygen will have -1, chlorine will have +1. If I talk about this single bond, again chlorine is more electronegative, so -1, this is +1. If I talk about this single bond between calcium and oxygen is more electronegative, so -1, +1. If I ask you, what is the charge present on this chlorine, you'll say +1. So +1 is the oxidation state of this chlorine right here, and -1 is the oxidation state of this chlorine right here. I'll say +2 is the oxidation state of this calcium right here, and simply -2 is the oxidation state of this oxygen right here. Remember this at the same time. Yes? Yes, very, very, very simple. Okay. Let's move on to a few more structures, guys. Structure of BASCN whole twice. Okay. Let's get to know the structure of BASCN whole twice as well. This is S, this is C, this is triple bond N. This is S, this is C, this is triple bond N. This is the structure of BASCN whole twice. Yes. Now, guys, let's get to know the oxidation states of different elements right here in this compound. First thing, if I consider this triple bond between carbon and nitrogen, let me tell you, nitrogen is more electronegative element than the carbon. So nitrogen will attract the 3 bonded pair of electrons towards itself. So nitrogen will have -3 charge. At the same time, carbon will have +3 charge. At the same time, guys, if I consider this triple bond between carbon and nitrogen, again nitrogen will have -3, carbon will have +3. If I consider this single bond, let me tell you, sulfur is more electronegative than carbon. So sulfur will have -1, carbon will have +1. Again, right here, sulfur will have -1, carbon will have +1. If I consider this single bond, again sulfur is more electronegative than barium. So sulfur will have -1, barium will have +1. If I talk about this single bond, sulfur will have -1, barium will have +1. If I ask you, what is the charge present on this barium right here? It's going to be +2. What is the charge present on this sulfur right here? It's going to be -2. What about the charge present on this sulfur right here? It's going to be -2. What about this carbon? It's going to be +4. What about this carbon? It's going to be +4. What about this nitrogen? It's going to be -3. What about this nitrogen? It's going to be -3. So people, you got the oxidation states of different elements right here in this compound. Yes, very, very, very simple. Okay. Yes, Priya. Yes, 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 yes. You're right. You are right. Yeah. Okay, let's move on to a few more structures, guys. Let's move on to a few more structures. This is H2SO4. All of you must be knowing its structure, so I'm not going to draw it. Okay, this is very simple. H2SO4, sulfur की oxygen state +6 होगी यहाँ पे, yeah? Correct? Now, let's talk about few more compounds, guys. Let's talk about few more compounds right here. These are the acids of phosphorus, right? First of all, I'll be drawing H3PO2 structure. Right here, I'll be drawing H3PO3 structure, and right here, I'll be drawing H3PO4 structure, and right here, I'll be drawing the structure of H3PO5. Yes, and with this, our structures will be over. With this, our structures will be over. Then I'll move on to one more important topic. That's what we call as equivalent mass. Yes? Yes? Understand, guys. See, H3PO2. First of all, I'm going to draw P double bond O everywhere. I'm going to draw P double bond O everywhere. Yes. I'm going to draw P double bond O every single times right here. Okay. Now, guys, total I have 2 oxygens. Out of 2 oxygens, I have used 1 oxygen. So one more will be here. With this, I'll attach hydrogen. And since there are 3 hydrogens, I have used 1. So it's going to be 1 more. It's going to be 1 more. This is the structure of H3PO2, right? So I have 3 oxygens in total. Out of 3, I have used 1. So there are 2 more left like this. And attach 2 hydrogens with these oxygen and 1 hydrogen is left. Attach that directly with the phosphorus. Yes? Yes? Now, guys, understand. If I talk about H3PO4, it's going to be like this. It's going to be like this. Yes. This is the structure of H3PO4 right here. This is the structure of H3PO4. And what about the structure of H3PO5? H3PO5 structure is going to be like this. There'll be one peroxide linkage right here, guys. This one, yeah? This is the structure of H3PO5. Yes. You can calculate the oxidation state of every element right here. Okay. Absolutely. Right? It's not my birthday, guys. It's not my birthday. My birthday is on 6th April, okay? Remember that. It's on 6th April, yeah? Okay, so first of all, let's calculate the oxidation state of phosphorus right here. So in order to calculate the oxidation state of phosphorus, let me consider this double bond first of all. Oxygen is more electronegative than phosphorus. So by means of this double bond, oxygen will have -2, phosphorus will have +2. By this single bond, oxygen -1, phosphorus +1. Now people, let me tell you, phosphorus is more electronegative than hydrogen. So phosphorus will have -1, hydrogen +1. What about this one? What about this bond? Phosphorus -1, hydrogen +1. People, what is the net charge present on this phosphorus right here? Net charge present on this phosphorus is going to be +1. Yeah. Yes. Now guys, what about this phosphorus right here? Again, due to this double bond, phosphorus will have +2 charge. Yes, due to this double bond, because oxygen is more electronegative. What about this single bond? Oxygen -1, phosphorus +1. What about this one? Oxygen -1, phosphorus +1. What about this bond? Let me tell you, phosphorus is more electronegative, so phosphorus -1, hydrogen +1. Now people, let me tell you, it's oxidation state +2, +1. That means +3, +4, -1. So +3 is the oxidation state of phosphorus right here in this compound. Yes. Yes. Now guys, let's talk about the structure of this. It's simply going to be +5 because on every side there is oxygen. What about the oxidation state of phosphorus over here? It's going to be +5. You can calculate it at the same time. Yes, you can do that, right? Right? Okay, let's move on. Okay, there is one more structure pending right here, K3CrO8. Yes. How old am I? I'll turn 26 on 6th April, yeah? I'll turn 26 on 6th April. Okay? So should I be expecting some gift from you? Yeah? Yes, Amrita? Okay, let's talk about K3CrO8. Okay? See guys, this is Cr, this is oxygen, this is oxygen, this is a single bonded linkage right here. This is oxygen, this is oxygen, this is oxygen, this is one peroxide, this is one more peroxide, this is one more peroxide. Over here we have got potassium, over here we have potassium, there is one more potassium right here. Okay? Yes. Now guys, let's try to calculate the oxidation state of chromium right here. On every side, chromium is attached with the oxygen by means of a single bond, and there are 5 single bonds. So I can directly say the oxidation state of chromium right here is +5. Yes, because oxygen is more electronegative than chromium. Yes. Very simple, correct? Yes. Guys, I'm not married, okay? मेरी शादी चैट बॉक्स में मत करा दो, ठीक है? यहाँ पे दिमाग यहाँ पे रखो, ठीक है? बाकी की बातें बाद में. Yes? Okay. All right, guys. See, have a look. If I talk about this single bond, oxygen -1, chromium will have +1. What about this single bond? Again, oxygen -1, chromium +1. What about this single bond? -1, +1. What about this single bond? -1, +1. What about this one? -1, +1. So net +5 charge. So +5 is the oxidation state of chromium right here. Yes? Okay. So with this, guys, our structures are over. Now let's get to know the actual stuff. We are going to enter into the redox properly now. Okay, we are done with the basics. We have talked about something called as oxidation state. We got the rules to calculate oxidation state. We saw some different structures which you guys are going to remember. Now let's enter into oxidation reduction. Let's enter into the N factor calculation right here. Okay. All right. So people, how do we define oxidation? Okay, how do we define oxidation? You would have studied oxidation. I mean, in your class 10th, class 11th, everywhere you would have studied oxidation. But people, you don't have to remember all this. Okay? Still, oxidation means loss of electrons, removal of hydrogen, addition of oxygen, addition of more electronegative element. Similarly, reduction, gain of electrons, addition of hydrogen, removal of oxygen, removal of... You don't have to remember all this. You just have to remember one thing, which I'm telling you right here. Just wait a second, guys. Just wait a second. Yes, this is something which you have to remember. Remember, in oxidation, the oxidation state of element always increases, and during reduction, the oxidation state of element always decreases. Only thing which you guys are supposed to remember right here. For example, I've got a reaction like this. General reaction I'm talking about. Okay. For example, A plus B, it gives A positive plus B negative. Yes, I'm assuming assuming this A and B right here to be present in their standard states, and when the element is present in its standard state, its oxidation state is taken to be 0. So I would say oxidation state of A and B right here will be 0. Absolutely. What is the charge present on this A right here? It is +1. What is the charge present on this B right here? It is -1. Yes. Now people, you would have noticed one thing. Is the oxidation state of A increasing? Absolutely. The oxidation state of A is increasing. Is the oxidation state of B decreasing from 0 to -1? Yes, oxidation state of B is decreasing from 0 to -1. Let me tell you, increase in the oxidation state of element is what we call as oxidation. So I would simply say A is undergoing oxidation right here, and since there is the decrease in the oxidation state of B, and decrease in the oxidation state is what we call as reduction. And people, let me tell you, that substance which undergoes oxidation, that's what we call as reducing agent, and that substance which undergoes reduction, that's what we call as oxidizing agent. This is very simple, which I want you guys to take a note of. Yes. At the same time, if I'm considering one more reaction with this, everything will get clear to you. Let's say I've got a reaction like this, a general reaction which I'm taking right here, okay, and I'm assuming this A and B right here present in their elemental states, standard states, so its oxidation state is going to be taken as 0. What is the charge present on this A right here? It's +1. What is the charge present on this B right here? It's -1. So people, if I ask you, is the oxidation state of A increasing or decreasing? The oxidation state of A is changing from 0 to +1. So the oxidation state of A right here is increasing. Increase in oxidation state is what we call as oxidation, and that substance which undergoes oxidation, that acts as the reducing agent. So A2 will be my reducing agent right here. And similarly guys, oxidation state of B is decreasing from 0 to -1, and decrease in the oxidation state is what we call as reduction. So this B2 right here is undergoing reduction, and we know any substance which undergoes reduction, that's what we call as oxidizing agent. Yes. So this is how we identify which one is the oxidizing agent and which one is the reducing agent right here. Yes. Yes. Okay. Now guys understand few more things. Yes, this is something which I told you, oxidizing agent and reducing agent. I just gave you the idea of how to identify which one is the oxidizing agent and the reducing agent. Now what this oxidizing and reducing agent actually is. Remember guys, oxidizing agent is the one which oxidizes others but itself undergoes reduction. Oxidizing agent is the one which oxidizes others but itself undergoes reduction. Similarly, reducing agent is the one which reduces others but itself undergoes oxidation. Yes, one more time I'm repeating the same. Oxidizing agent is the one which oxidizes others but itself undergoes reduction. Yes, and reducing agent is the one which reduces others but itself undergoes oxidation. Remember it at the same time. Let me give you its examples, guys. Let me give you its examples. Understand properly what I'll say. Okay, I'm assuming this magnesium to be present in its elemental state, native state, standard state. So its oxidation state will be 0. Oxygen right here is again present in its standard state. So 0. What about the oxidation state of magnesium right here? It's going to be +2. What about the oxidation state of oxygen right here? It's going to be -2. Yes. Very simple. So guys, is the oxidation state of magnesium increasing or decreasing? Oxidation state of magnesium is changing from 0 to +2. So oxidation state of magnesium is increasing, and increase in the oxidation state is what we call as oxidation. So this magnesium is undergoing oxidation right here, and any substance which undergoes oxidation, that's what we call as a reducing agent. Very simple. Yes. Now people, at the same time, is the oxidation state of oxygen increasing or decreasing? Understand properly. Oxidation state of oxygen is changing from 0 to -2. So oxidation state of oxygen is decreasing. Decrease in oxidation state is what we call as reduction. So this O2 is undergoing reduction right here. If it is undergoing reduction, it will be acting as the oxidizing agent. And at the same time, reducing agent is also called as reductant. Okay, and oxidizing agent is also called as oxidant. Yes, remember this at the same time. Sometimes examiner might confuse you from these terminologies as well. Yeah, remember these. Yes, oxidant and reductant. Yes. Remember these two as well. Okay, this is one more reaction, guys. In this reaction, we need to identify which one is the oxidizing agent and which one is the reducing agent. You can easily do it. You can easily do it. Understand. First, what I'll be doing, I'll be calculating the oxidation state of every element right here. And once I get to know the oxidation state of every element right here, you can easily you can easily tell me which one will be my oxidizing agent and which one is going to be my reducing agent. Very, very, very simple. Yeah. Understand. The oxidation state of iron is going to be +2. When you will calculate it by means of formula, you can do that. Yeah, I've showed you that. Oxidation state of oxygen is -2. What about oxidation state of this Mn right here? It's going to be +7 when you will calculate it. What about the oxidation state of this chlorine right here? -1, hydrogen +1. This oxygen -2. Yes. What about this iron? You can calculate it. 2x - 6 is equal to 0. So it's going to be +3. Oxidation state of oxygen -2. Oxidation state of Mn right here will be +2. Oxidation state of chlorine -1. Oxidation state of oxygen -2. Hydrogen +1. First of all, if you would have noticed one thing, the oxidation state of oxygen is not changing at all. The oxidation state of oxygen is not changing at all. So I have got nothing to do with this oxygen. And at the same time, oxidation state of hydrogen is also not changing at all. So I have got nothing to do with this hydrogen at the same time. So what all elements are there whose oxidation states change? That is going to be my concern right here. Understand. The oxidation state of iron is changing from +2 to +3. So I will say the oxidation state of iron increases. If oxidation state of iron increases, I'll say this compound will be undergoing oxidation, and if this compound undergoes oxidation, it will be acting as the reducing agent. Yes, or I'll be calling it as the reductant. Similarly, the oxidation state of manganese is changing from +7 to +2. The oxidation state of manganese is decreasing. Decrease in the oxidation is what we call as reduction. So I will say this compound MnO4 negative right here is undergoing reduction. If it is undergoing reduction, it will be acting as the oxidizing agent. So very simple thing by means of which we can identify which substance undergoes oxidation, which substance undergoes reduction. Yes? Okay. Now people, last example by means of which everything will get clear so that I can move on to the actual topic which we have to discuss, that is the equivalent mass. Yeah? Yes, understand guys, there is no charge present on this zinc right here, its oxidation state is 0. The charge present on this copper is +2. The charge present on this zinc is +2. The charge present on this copper is 0. Yes, is the oxidation state of zinc increasing or decreasing? Increasing. Increase in oxidation state is what we call as oxidation, and any substance which undergoes oxidation, that will be my reducing agent. Yeah. Copper from +2 to 0, from +2 to 0, decrease in oxidation state, and decrease in oxidation state is what we call as reduction, and any substance which undergoes reduction, that is going to be my oxidizing agent. Yeah, isn't it simple guys? Isn't it simple? Let me know in the chat box. Yes, let me know in the chat box. Let me know in the chat box. Let me know in the chat box fast. Yes, I'm moving on to the actual stuff. Yeah, do hit the like button if you got the concept. Yes. Ubi walaikum salam. नहीं यार मैंने अभी dinner नहीं करा. I'll have the dinner once the session ends. Yeah. Let me know in the chat box, guys. Let me know in the chat box. I'm from Kashmir. Yeah. Hi, Yesh. What's up? Long time, man. Long time. Where have you been, bro? Thank you, MK. Thank you. All right, so let's move on and let's get to know something really, really interesting and fascinating, which is something which we call as equivalent mass. So people, let me see the Josh of the session first. Are you super duper excited? Yes. Let me know in the chat box. Let me know in the chat box if you are super duper excited. Yes. Let me know fast. Let me know fast. Yes. Is the Josh still high? Is the Josh still high? Yes. Wonderful. Yes, I know. Sorry, sir. Absolutely. Wonderful, guys. Oh, Janan is saying the Josh is proportional to you, sir. Okay, fine. That's great. That's great. That's wonderful. All right, let's move on, guys. Let's move on and talk about something really interesting, which is what we call as equivalent mass. Okay, what is this equivalent mass all about? Understand properly what I'll say. Let's talk about its definition first. Equivalent mass is defined as the mass of the substance which can combine or displace. The mass of the substance which can combine or displace. either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver. Yes. This is the simplest way by means of which we can define equivalent mass. Now, what all things can we get from here? How can we master this concept of equivalent mass? For that, you need to understand this definition, okay? For that, you need to understand this definition. First of all, in order to calculate the equivalent mass of any substance, I need to check what is the mass of substance which would have combined or displaced 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver. Yes, very simple concept this is, guys. Very simple concept. That mass of the substance which can displace or combine either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver. Yes, let's master this concept in detail. Let's master this concept in detail, okay? Understand, guys. Understand properly what I'll say, okay? See, first of all, this is one balanced chemical equation which I have. This is one balanced chemical equation which I have, okay? Understand. What is the stoichiometric coefficient right here? I'll say 1. What about the stoichiometric coefficient right here? It's 1/2. Can I say 1 mole? Can I say 1 mole of magnesium? Can I say 1 mole of magnesium combines with half moles of oxygen? Yes. 1 mole of magnesium combines with half moles of oxygen. Yes, I can say that, right? Now, guys, understand what I'll say. 1 mole of magnesium. People, what is the mass of 1 mole of magnesium? Mass of 1 mole of magnesium, that's what we call as molar mass of magnesium. Yes, people, molar mass of magnesium is 24 grams. So I can simply say 24 grams of magnesium. Yes, it combines with, okay, half mole of oxygen. Okay, half mole of oxygen. People, do you know one thing? Do you know one thing? Do you know the molar mass of oxygen? Molar mass of O2 is 32 grams. That means mass of 1 mole of O2 is 32 grams. But right here, I have only half mole. So what is going to be the mass of half mole of oxygen? Isn't it going to be 16 grams? Yes. Isn't it going to be 16 grams? I can say that, right? I can say that, yeah. Very simple. Now, guys, can I write a statement like this? Can I say 16 grams of oxygen, 16 grams of oxygen combines with 24 grams, combines with 24 grams of magnesium? Yes. So I can say 1 gram of oxygen, 1 gram of oxygen combines with 24 divided by 16 grams of magnesium. Yes. So I can say 8 grams of oxygen, 8 grams of oxygen combines with 24 divided by 16 multiplied by 8. Value will be simply 12 grams of magnesium. So can I say, guys, simple thing over here. Can I say 12 grams of magnesium have combined with 8 grams of oxygen, and that mass of the substance, which would have combined with 8 grams of oxygen, that's what we call as equivalent mass of the substance. Yeah, very simple. So I can say equivalent mass of magnesium right here in this reaction is simply 12 grams. Yes, so I can say 12 grams of magnesium have reacted with 8 grams of oxygen, or you can say 1 gram of hydrogen, or you can say something like 35.5 grams of chlorine or something like that. Yeah, very simple, correct? Now, guys, let me take one more reaction by means of which your concepts will get clear to you. Understand that as well. People, what is the stoichiometric coefficient of nitrogen right here? It is 1. What about the stoichiometric coefficient of hydrogen right here? It is 3. Can I simply say 1 mole of nitrogen, 1 mole of nitrogen reacts with or combines with 3 moles of hydrogen? Yes, I can say that. Yes, right? Now, guys, 1 mole of nitrogen. What is the mass of 1 mole of nitrogen? Mass of 1 mole of nitrogen, that's what we call as molar mass of nitrogen. And what is the molar mass of nitrogen? N2, that is 28 grams. So instead of 1 mole of N2, I can say 28 grams of nitrogen simply. It combines with 3 moles of hydrogen. Yes, people, what is the mass of 1 mole of hydrogen? What is the mass of 1 mole of H2? You will say 2 grams. You will say 2 grams. Yes, 2 grams is the mass of 1 mole of this hydrogen. But how many moles of hydrogen do we have? We have 3 moles. So 3 moles will have the mass of 6 grams. So I can say simply like this. I can say 28 grams of nitrogen combines with 6 grams of hydrogen. Or people, I can take the reverse of it. I can say 6 grams of hydrogen. 6 grams of hydrogen combines with 28 grams of nitrogen. Yes, I can say that. Can I simply say 1 gram of hydrogen should combine with 28 divided by 6 grams of nitrogen? Yes, I can say that. Yes, so 28 divided by 6 means, guys, how much that is? Just a second, equivalent mass of N2. Just erase this part, guys. Erase this over here. Erase this over here. Okay. See, guys, what I got to know? I got to know something like this. 6 grams of hydrogen combines with 28 grams of nitrogen. Yes. So 1 gram of hydrogen would have combined with 28 divided by 6, which is simply 14 divided by 3 grams of nitrogen. And people, I can say something like this. I can say 14 by 3 grams of nitrogen would have got combined with 1 gram of hydrogen, and that mass of substance which combines with 1 gram of hydrogen, that's what we call as equivalent mass. So equivalent mass of nitrogen right here is simply going to be 14 divided by 3 grams. Yes, let me know in the chat box if you got the concept of equivalent mass so that I can talk about this a bit more in detail right here. Let me know in the chat box fast. Let me know fast. Yes. Wonderful. Great. Great, guys. Sarvendra, you can take the video a little back, bro. It'll be automatically a replay, yeah? Just use a common sense, bro. Use the common sense, yeah? Video thoda पीछे ले ले, बस हो गया. Yes. Let's move on. People, there is one simple formula by means of which you can calculate the equivalent mass of any substance. There is one simple formula which you guys are supposed to remember in order to calculate the equivalent mass of any substance. Let me tell you, equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of substance. Yes, remember, equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the substance. Now the point is, what is this n factor all about? How do we calculate this n factor right here? And people, at the same time, let me tell you, equivalent mass is expressed in grams. Equivalent mass is expressed in grams. Let me tell you, equivalent mass is nothing, molar mass of the substance divided by n factor of the substance. Now the point is, how do we calculate the n factors of different substances? And once we get to know the n factors of different substances, we can easily calculate equivalent mass of anything right here. Yes, so let's get started with something called as calculation of n factor right here. Okay, the first thing which I'm talking about right here, that is n factor of ions, right? How do we calculate n factor for ions? Simply, guys, n factor of ions is always equal to magnitude of charge right here. So people, this Na positive, this is my ion. What is the charge present on it? +1. Just take the magnitude of it, it's going to come as 1. So 1 is going to be the n factor of this ion. Similarly, what is the charge present on Mg di positive? It's 2. Just take the mod of it, magnitude of it. Magnitude of charge will give you the n factor of Mg di positive. What about the charge present on this aluminum right here? It's +3. Take the magnitude of it, it's going to come as 3. So 3 is the n factor of Al tri positive right here. And once you get the n factors of these ions, you can easily calculate their equivalent masses. How? Very simple. Simple, guys. Just divide the molar mass of the substance by the n factor. Just divide the molar mass of the substance by the n factor. Just divide the molar mass of the substance by its n factor. You'll be getting the equivalent masses of different substances right here. And people, there is one thing where you might get confused. What is that? Remember, if I have got sodium or I have got Na positive, remember, due to the presence of the charge on the atom, there will be no effect on the molar mass. Remember, molar mass of the substance is independent of the charge present on it. Yes, I have got chlorine, I have got Cl negative, both the ones will have same molar mass. I have got Na, I have got Na positive, both the ones will have same molar mass. So molar mass is independent of the charge present on the ion. Remember this at the same time. Okay, let's move on, and let's get to know how to calculate n factors of salts. Yes, how do we calculate n factors of salts? N factor of salt is always equal to LCM of charge present on cation and anion. Understand, guys, this is a salt right here, NaCl. What is the charge present on Na? +1. What is the charge present on chlorine? -1. If I take the LCM of 1 and 1, okay, I'm taking the LCM of charges present on cation and anion, it's going to come as 1. And whatever is the n factor of the, whatever is the LCM of of charge present on cation and anion, that's what I'll be calling as the N factor of the salt. And once you get to know the N factor of the salt, you can easily calculate its equivalent mass. How? You'll say equivalent mass of NaCl is equal to molar mass of NaCl divided by N factor, that is 1. So 58.5 grams is the equivalent mass of NaCl right here. Similarly, the charge present on Mg is +2, the charge present on oxygen is -2. Just take the LCM of 2 and 2. LCM of 2 and 2 is 2. So N factor of MgO right here is 2. Once you get to know the N factor of MgO, which is 2, divide its molar mass by the N factor, you will get its equivalent mass. Now we will talking about Al2SO4 whole thrice. Let me tell you guys, the charge present on Al right here is +3. The charge present on sulfate is -2. You can simply take the LCM of 3 and 2. LCM of 3 and 2 is 6. So I'll say N factor of this substance, this compound right here is 6. Once you get to know its N factor, which is 6, divide the molar mass of the compound by 6, you can get the equivalent mass. Yes? Let me know. Yes, Balaji, this is the revision series, bro. Yes. Let me know, guys, if it's clear to every single guy so that I can move on and talk about few more interesting things right here. Yes, I want every one of you to tell me right now. Yes. Okay, let's move on to something else. How do we calculate the N factors of acids? Okay, let me tell you guys, N factor of acid is always equal to the basicity of the acid. And what is the basicity of the acid? The number of H positive ions an acid donates when dropped in water. The number of H positive ions an acid donates in water, that's what I call as the basicity of the acid. For example, I've got HCl. If I drop this HCl into water, can I say it will give away 1 H positive? Can I say it will donate 1 H positive? And the number of H positives an acid donates, it defines the basicity of the acid. And whatever is the basicity of the acid, it's going to be its N factor. Yes. Now at the same time, if I talk about H2SO4, okay, if I'll drop it into water, can I say it will donate 2 H positives? Yes, and the number of H positives an acid donates, it defines its basicity. So basicity of this H2SO4 right here is 2, so its N factor is simply 2. And once you get to know its N factor, which is 2, divide its molar mass by its N factor, you'll be getting the equivalent mass. Yes, very simple. Aksa, just wait for it. We'll be talking about that in a while. Yes. Talking about the oxalic acid, guys. Oxalic acid, H2C2O4. If I drop this H2C2O4 in water, it will give away 2 H positives. Yes, it will donate 2 H positives. And the number of H positives an acid donates, it defines its basicity. So its basicity right here is 2. So its N factor is simply 2. Similarly, what is the N factor right here? It's going to be 3. Okay. Once you get to know the N factor of acids, you can easily calculate their equivalent masses, right? By simply dividing the molar masses by the N factors. Yeah. Now people, understand few more important things. Okay. See guys, remember this statement, which is very important. An acid donates only that H positive which is connected to more electronegative element like oxygen, like fluorine, like nitrogen. Remember, an acid only donates that H positive which will be connected to the more electronegative element like oxygen, fluorine or nitrogen. Understand, if I'll take H3PO2, what I'm thinking right here is, a common man will think like this: H3PO2, if I'll drop it into water, it should lose 3 H positives, it should donate 3 H positives, so its N factor should be 3, its N factor should be also 3, its N factor should be also 3, its N factor should be also 3, but the case is reverse. I told you, an acid donates only that H positive which is connected to more electronegative element. Yes, for example, oxygen, fluorine, nitrogen. Now people, first thing, you should know the structures of these compounds, then only you can talk about these. Yes, understand. If I talk about the structure of H3PO2, which I told you just now few minutes back, this is the structure of H3PO2. Yes, this is the structure of H3PO2. Can I say only one hydrogen is attached to more electronegative element like oxygen, and acid donates only that H positive which is connected to more electronegative element. So this acid will donate this hydrogen in the form of H positive. So this acid donates only one H positive. Its basicity is going to be 1. Its N factor is going to be 1. Yes. Yes. Now people, what about H3PO3? If I talk about the structure of H3PO3, it is somewhat like this. This is the structure of H3PO3. This is the structure of H3PO3. Now people, this hydrogen and this hydrogen, these two hydrogens are attached with the more electronegative element like oxygen. So this compound, this acid is going to donate 2 H positives, and the number of H positives an acid donates, it defines its basicity. So I will say the basicity of this acid right here is 2. So its N factor is 2. If it is N factor is 2, you can calculate its equivalent mass by dividing the molar mass of the compound by its N factor. Yes, very simple. Now people, talking about H3PO3, as you all must be knowing its structure is like this. This is H3PO3. This is H3PO3. So I would say right here, this hydrogen and this hydrogen, all these 3 hydrogens are attached to more electronegative elements. So it's going to donate all these 3 hydrogens in the form of H positives. So I'll say the N factor, the basicity of this acid right here is again 3. Similarly, if I talk about H3PO5 structure is somewhat like this, which I showed you a few minutes back. Yes, this is the structure of H3PO5. Yes, so I will say 3 hydrogens are attached with 3 oxygen atoms. So it's going to donate these 3 hydrogens in the form of H positives. So its N factor is going to be 3. Yes, very simple. Once you get the N factors of these acids, you can divide their molar masses by their respective N factors. You'll be getting the equivalent masses of these acids right here. Yes. Now people, one more special case we have. What is that special case? N factor of boric acid is taken as 3. N factor of boric acid is taken as 1. Okay, why is that? Understand properly. See, if I talk about the structure of boric acid, it's going to be simply like this, as you all must be knowing. This is B, this oxygen, this hydrogen, oxygen, this hydrogen, this oxygen, this hydrogen. So people, as per this structure, can I say 3 hydrogens are attached to 3 oxygen atoms? So it should donate 3 H positives. Yes, it should donate 3 H positives. Its N factor should be 3. Its basicity should be 3. But that is not the case. N factor of this is 1. Its basicity is 1. What is the reason for that? Let me tell you guys. When I drop this oxygen into water, on this oxygen there are 2 lone pairs like this. Yes, people, if I ask you something like this, is this boron center the electron deficient center or electron rich center? You will say it has got only 6 electrons in its outermost shell, so it is going to be definitely electron deficient. If it is electron deficient, can I say if someone will give away the electrons, can I say it's easily going to accept those electrons? Yes, it is easily going to accept those electrons. Very simple. Now guys, one thing before talking about this case in particular, people, you might have heard about something called as coordinate bond. Yes, you might have heard about something called as coordinate bond. Coordinate bond is represented like this. If A is the donor atom, B is the acceptor atom, it's going to be represented like this. This is one way by means of which we can represent the coordinate bond, or I can represent the coordinate bond like this. Positive charge on the donor atom, negative charge on the acceptor atom. Now guys, this boron center, boron has got only 6 electrons in its outermost shell. So what it's going to do, it's going to act like the electron deficient center. So this oxygen, it is going to donate its lone pair, towards this oxygen, towards this boron. Since oxygen acts as the donor, it will have positive charge on it, and this boron will have negative charge on it. Why? Because boron acts as the acceptor atom. Yes. Now people, you have studied something like this. Positive charge on the electronegative element makes it highly unstable. Positive charge on oxygen makes it highly unstable. So what is going to happen? One of the bond will get broken down towards this oxygen, so that this oxygen can compensate this positive charge, so that this positive charge gets nullified. That's why one of the bonds will get broken down towards this oxygen, and this hydrogen will leave as H positive. So people, can I simply say only one hydrogen is donated right here, and the number of hydrogens which are donated, the number of H positives which are donated by the acid, it defines the basicity of the acid, and whatever is the basicity of the acid, that's what we call as the N factor of the acid. So remember, N factor of this boric acid right here, N factor of this boric acid right here, it is going to be 1. Why is that? Due to this mechanism right here. Let me know in the chat box if you got it in proper. Yes. So from now onwards, what you are going to remember, N factor of boric acid, it's not going to be 3, it's going to be 1. Yeah, very simple. Yeah. Yes, let's move on and let's talk about one more important statement right here. An acid donates. N factor of the acid. N factor of the acid depends on the type of the reaction it participates in. See guys, I have mentioned two important reactions right here. This is one reaction, this is one more reaction. People, if I want you guys to calculate the N factor of H2SO4 right here and N factor of H2SO4 right here, can we do that? Absolutely, we can do that. See guys, first of all, how do we define the N factor of the acid? That's N factor of the acid is equal to basicity of the acid. And how do we define basicity? The number of H positives and acid donates is what we call as basicity. Yes. Now guys, understand how many hydrogens do we have right here? 2. This H2SO4 is getting converted to NaHSO4. So it had 2 hydrogens. Right here it has got only 1 hydrogen. So people, can I say during its conversion from H2SO4 to NaHSO4, it has donated 1 H positive, and the number of H positives and acid donates, it defines its basicity, and whatever is the basicity of the acid, that defines its N factor. So N factor of H2SO4 right here is going to be simply 1. Similarly guys, how many hydrogens do we have right here? There are 2 hydrogens, and this H2SO4 is getting converted to Na2SO4, and during its conversion right here it had 2 hydrogens, but right here it has no hydrogen. So during its conversion, can I say it has lost 2 H positives, and the number of H positives lost by an acid defines its basicity, and whatever is the basicity of the acid, that defines its N factor. So N factor of H2SO4 right here is 1, N factor of H2SO4 right here is 2. So I can say equivalent mass of H2SO4 right here in this reaction is going to be molar mass of H2SO4 divided by N factor. So this is going to be the equivalent mass of H2SO4 right here, and equivalent mass of H2SO4 right here is going to be molar mass divided by N factor. Can I say equivalent mass of the same substance is different in different reactions? So remember, equivalent mass is a variable quantity. It is a variable quantity. Equivalent mass of the same substance changes on changing the reaction. Yes, I want you guys to take a note of it right here, which is very, very, very important. Okay. Now guys, let's get to know something called as N factor for bases. How do we define the N factor of bases? N factor of bases is simply the acidity of the base. Yes, whatever will be the acidity of the base, same is going to be the N factor of base. Yes, N factor of base is always equal to the acidity of the base. And how do we define the acidity of the base? That is the point. Let me tell you, the number of OH negatives a base donates, that defines the acidity of the base. Or I can say the number of H positives a base accepts, that's what we call as acidity of the base. Now what does that mean? Understand. First, remember, N factor for base is always equal to the acidity of the base. Yes. And how do we define the acidity of the base? Simple. Number of OH negative ions a base donates, or the number of H positives a base accepts. These are the 2 ways by means of which we can define the acidity of the base. And remember, whatever is going to be the acidity of the base, same is going to be the N factor of the base. Yes. Let's get to know about the examples which we have right here. Yes, see people, if I'll drop this NaOH into water, it will donate 1 OH negative. Yes, and similarly this, on dropping into water, it will donate 1 OH negative. On dropping this into water, it is going to give 2 OH negatives. On dropping this into water, it's going to give 3 OH negatives. On dropping this into water, this is FeOH whole thrice, it gives it's not 3 OH negatives, just a second, it's going to be 2 OH negatives, and it's going to be 3 OH negatives. Yes, and the number of OH negatives donated by the base, it defines the acidity of the base, and whatever is the acidity of the base, that defines the N factor of base. So I can say N factor of NaOH right here is 1, N factor of KOH right here is 1, N factor of MgOH whole twice right here is 2, CaOH whole twice right here is 2, FeOH whole thrice right here is 3. These are the N factors of different substances right here. And people, let me tell you, if you got to know the N factors of different bases right here, you can calculate the equivalent masses of these bases by simply dividing the molar masses of these bases by their respective N factors. Very, very, very simple. Okay. Now guys, there are 2 more compounds which I have taken right here. Understand that as well. NH3, it's a base. This compound right here, it is a base. Correct? Because NH3 on nitrogen, you have got a lone pair. Correct? If you have got a lone pair on this nitrogen can donate this lone pair, and any substance which can donate a pair of electron, that acts as the Lewis base, as you all must be remembering. Yes, people, if I'll drop this NH3 into water, in water you have got H positives. Can I say this H positive can attack this lone pair from this side? So can I say this base can accept one H positive, and the base, the number of H positives a base accepts, it defines the acidity of the base, and whatever is the acidity of the base, that's what we call as the N factor of this base. So N factor of NH3 right here is going to be 1. Yes, N factor of NH3 right here is going to be 1 because this base can accept one H positive over here. Similarly guys, if I'll drop this substance right here into water, can I say we have got 2 nitrogens, on this nitrogen a lone pair, on this nitrogen a lone pair. Can I say there are already H positive ions in the container? Can I say this H positive can attack the lone pair from this side, this H positive can attack the lone pair from this side? So I can say this base can accept 2 H positives, and the base accepting 2 H positives defines its acidity, and whatever is the acidity of the base, it defines its N factor. Yes, let me know in the chat box if it is clear to every single guy. Yes, let me know in the chat box if it is clear to every single guy. Yes. Now guys, few more examples. See, I have taken 2 reactions. One is ZnOH whole twice. One is ZnOH whole twice. Again, I've taken 2 reactions. Over here, I've taken ZnOH whole twice. Again, I've taken ZnOH whole twice. And I want you guys to calculate the N factor of ZnOH whole twice in both the reactions. You can easily calculate that. Right here, we have got 2 OH negatives, and this ZnOH whole twice, it is getting converted to ZnOHCl. People, over here we had 2 OH negatives, and during its conversion right here we have got only 1 OH negative. So during its conversion it has lost 1 OH negative, it has donated 1 OH negative, and the number of OH negative a base donates, that's what we call as acidity, and whatever is the acidity of the base, that's what we call as N factor. So N factor of this base right here is 1. Very, very, very simple. At the same time, if I talk about the N factor of ZnOH whole twice, right here it had 2 OH negatives right here, and it is getting converted to ZnCl2. In this ZnCl2 there is no OH negative. So during this its conversion, can I say it has donated 2 OH negatives, and the number of OH negatives a base donates, which defines the acidity of the base, and whatever is the acidity of the base, it defines the N factor of the base. So I can say N factor of ZnOH whole twice right here in this reaction is going to be 2. So people, N factor of the same substance is different in both the reactions. So I can again say N factor of the substance is a variable quantity. It changes on changing the type of the reaction. It changes on changing the reaction. Yes, so I can say equivalent mass of ZnOH whole twice is a variable. Equivalent mass is something which is variable, which can change on changing the reaction. Yes, let me know in the chat box guys if everything is clear to you or not. Let me know in the chat box. Let me know in the chat box if everything is damn clear to you or not. Let me know. Sachin, you can do one thing, bro. You can take the video a little back. It'll be automatically clear to you, yes? Hi, Yashwani. What's up? My health is getting better. Yes. Hakima. Yes. Hi, Faisal. Hello, Aryan. What's up, guys? How are you guys doing? I'm sure you guys are enjoying this session, yeah? Is that? Yes, Farooq, it's happening. Yes, it's happening. Yes. Walaikum salam. Yes, I get it, bro. I get it. Thank you, Joseph David. Thank you. People, should we start again, yeah? Yes. Faisal, every day, every night at 11, I take the regular sessions on this channel, so you can attend that, yeah? Yes, Farooq, I can see 1 hour and 45 minutes are done. नहीं वासु मेरी शादी अभी नहीं हुई, ठीक है? I'm just 25, bro. Okay, let's move on and talk about how do we calculate the N factors of different oxidizing and reducing agents. Yes? Okay. See guys, understand properly what I'll be saying. N factor of the oxidizing or reducing agent is always equal to the number of moles of electrons, or you can say it like this, the number of electrons exchanged per mole of the oxidizing or reducing agent. Now what does that mean? What does that mean? It looks a bit, confusing. Yes, let's get to know it properly. See guys, understand properly what I'll say. First of all, I'm going to take a general reaction like this. A plus B, it gives A positive plus B negative. Yes, this is one reaction which I took right here. I'm going to take one more general reaction like this. A2 plus B2, it gets converted to twice A positive plus twice B negative. This is one more general reaction which I took over here. Now guys understand. I'm assuming this A and B right here to be in their elemental states. So their oxidation state is going to be 0 and 0. So people, the charge present on this A right here is +1, charge present on this B right here is -1. Now people understand, is the oxidation state of A increasing or decreasing? It is definitely increasing. Increase in the oxidation state is what we call as oxidation. So I must say A is undergoing oxidation, and any substance which undergoes oxidation, that acts as the reducing agent. Yes, very simple. At the same time, the oxidation state of B is changing from 0 to -1. So oxidation state of B is decreasing. Decrease in the oxidation state is what we call as reduction, and any substance which undergoes reduction, that's what we call as oxidizing agent. Yes, so I got to know this one is my reducing agent, this one is my oxidizing agent. Now the point is, how do I calculate their N factors? How do I calculate the N factor of this reducing agent and this oxidizing agent right here? See guys, very simple concept I'm going to teach you right here. Okay, see, in order to calculate the N factor of A, I simply need to calculate change in the oxidation state of A. Change in the oxidation state of the oxidizing or reducing agent is what we call as N factor. Understand what I'll say? See, can I say this 0 is the initial oxidation state of A? Can I say this +1 is the final oxidation state of A? In order to calculate the N factor of A, I need to calculate the change in the oxidation state of A, which is the final oxidation state minus initial oxidation state. Value will come as 1. So N factor of A right here will be simply 1. Similarly, in order to calculate the N factor of B, I can say this is the initial oxidation state of B. I can say this is the final oxidation state of B. So N factor of B, how will I be calculating that? N factor of B will be simply mod of change in the oxidation state of B, which will be final oxidation state of B -1 minus initial oxidation state of B 0. The value is going to come as 1. So 1 is the N factor of B right here. Isn't it simple? Isn't it simple? Absolutely guys. Now similarly, I'm assuming this A2 and B2, I'm assuming this A and B right here to be in their elemental states. So their oxidation states will be taken as 0. This is 0. This is 0. What is the charge present on this A right here? It is +1. What is the charge present on this B right here? It is -1. So people, if I ask you, is the oxidation state of A increasing or decreasing? It's increasing. Increase in the oxidation state is what we call as oxidation, and any substance which undergoes oxidation, that's what we call as reducing agent. Yes. At the same time, the oxidation state of B2 is decreasing from 0 to -1. Decrease in the oxidation state is what we call as reduction, and any substance which undergoes reduction, that's what we call as oxidizing agent. Now guys, in order to calculate the N factor of A2 and B2 right here, what I'll be doing, again I'll be calculating the change in the oxidation state, N factor of A2, change in the oxidation state of A, which is going to be final oxidation state of A. This is the final oxidation state of A. This is the initial oxidation state of A. Final oxidation state of A minus initial, value will come as 1. But let me tell you, this one is the change in the oxidation state for one atom of A. But I have two atoms, so I'm multiplying it by 2. The values come as 2. So I'll say N factor of A2 right here in this reaction is simply 2. Yes? Yes. Now people, similarly, n factor of B2 in this reaction. Again, I need to calculate change in the oxidation state of B. So I'll say this is the initial oxidation state of B. This is the final oxidation state of B. Calculate the change. Final minus initial. Final is -1. Initial is 0. Take the mod. Value will be coming as 1. But this one is the change in the oxidation state for one atom of B. But I have two atoms. So I'm multiplying it by 2. The value is going to come as 2. So 2 is the n factor of B2 in this reaction. Isn't it simple? Isn't it simple? Yes, absolutely, guys. It is very, very, very simple. Okay. Now, guys, understand. Let's talk about some common oxidizing and reducing agents right here. Let me tell you, guys, KMnO4. Let me tell you about KMnO4. KMnO4 acts as the oxidizing agent and it shows different reactions at different mediums, right? Either you write KMnO4 right here or you can write MnO4 negative. It's one and the same thing. And people, this KMnO4, this MnO4 negative, in acidic medium, it gets converted to Mn positive. In neutral medium, it gets converted to MnO2. And in basic medium, it gets converted to MnO4 negative. Now, what is interesting right here? Have a look. Have a look, guys. The oxidation state of Mn right here is +7. The oxidation state of Mn right here is +2. Right here it is +4. Right here it is +6. Yes. Very simple. Understand, guys. In acidic medium, the oxidation state of Mn changes from +7 to +2. So I'll be calling this as the initial oxidation state. I'll be calling this as the final oxidation state. If I need to calculate the n factor of KMnO4, n factor of MnO4 negative in acidic medium, I'll be simply calculating change in the oxidation state, which is going to be final oxidation state, which is +2, minus initial oxidation state, which is +7. Take the mod, value will come as 6, 7. Value will come as 5. So 5 is the n factor of KMnO4 or MnO4 negative in which medium? In acidic medium. Similarly, in neutral medium, +7 changes to in neutral medium. The oxidation state of Mn changes from +7 to +4. So this is going to be the final oxidation state. This is going to be the initial oxidation state. So in neutral medium, if I want to calculate the n factor of this KMnO4, of this MnO4 negative right here, it's going to be final oxidation state minus initial oxidation state. Value will be coming as 3. So 3 is the n factor of KMnO4 or MnO4 negative right here in this reaction. Similarly, guys, in basic medium, the oxidation state of Mn changes from +7 to +6. So +6 is the final oxidation state of Mn. So +7 is the initial oxidation state. Just calculate the change in the oxidation state. It's going to be final oxidation state of Mn minus initial oxidation state. The value is going to come as 1. So this one is the n factor of KMnO4, or you can call it as MnO4 negative in basic medium right here. So remember, n factor of KMnO4 in acidic medium is 5, in neutral medium it is 3, in basic medium it is 1. Okay. Now guys, few reactions which I want you guys to remember. Okay, I'm going to write few things right here. Okay, remember, guys, KMnO4 in acidic medium, it converts Fe dipositive to Fe tripositive. Remember, KMnO4 in acidic medium, it converts Fe dipositive to Fe tripositive. Now, if I want to write the reaction, you don't have to remember the reaction. You just have to remember one thing. It converts Fe dipositive to Fe tripositive. Now, I'll show you how to write the reaction. I'll be simply saying your KMnO4, or you can write MnO4 negative. MnO4 negative. It converts what? It converts Fe dipositive. In which medium? In acidic medium. It converts KMnO4, it converts Fe dipositive in acidic medium to Fe tripositive, and itself in acidic medium it gets converted to Mn dipositive, and with this you'll be adding some water as well. This is the reaction. You don't have to remember this. You just have to remember one thing, that KMnO4 converts Fe dipositive to Fe tripositive. Very, very, very simple. Yeah. Yes. Now, guys, one more thing. This is the first reaction. You don't have to remember the reaction. Just remember one thing. This KMnO4, it converts Fe dipositive to Fe tripositive in acidic medium. Number 1. Number 2, it converts oxalate ion to carbon dioxide. You can simply write the reaction. You can say MnO4 negative. It converts oxalate ion. In which medium? Acidic medium. To carbon dioxide. It converts oxalate ion to carbon dioxide, and in acidic medium, MnO4 negative gets converted to Mn dipositive and add some water molecules. Just done. Yes. Now, people, similarly, one more reaction. It converts I negative to I2. Yes, it converts I negative to I2. Your MnO4 negative or KMnO4, it converts I negative in acidic medium to I2, and itself gets converted to Mn dipositive. Just add some water molecules. Reaction is done. Yes. Yes. Now people, at the same time, it converts H2S to S. Yes, this is the reaction you can easily write now. MnO4 negative, it converts H2S in acidic medium to sulfur and itself gets converted to Mn di positive and adds some water molecules. You don't have to remember the reaction. Just remember one thing, your KMnO4, it converts Fe di positive to Fe tri positive in acidic medium. It converts oxalate ion to carbon dioxide. It converts H2S to sulfur. Rest you can write the reaction on your own. You don't have to remember these reactions. And similarly guys, it converts hydrogen peroxide to O2 right here. It converts hydrogen peroxide to O2 right here. Your KMnO4, your MnO4 negative, it converts H2O2 in acidic medium to O2 and itself gets converted to Mn di positive and adds some water molecules. Done and dusted. Yes. Now people, one more reaction. It converts Sn di positive to Sn plus 4, Sn di positive to Sn plus 4. So remember, KMnO4, it converts Sn di positive in acidic medium to Sn plus 4 and itself gets converted to Mn di positive, adds some water molecules. Done. There is one more reaction left. It converts SO2 to SO4 di negative. In the same way, you can write this reaction as well. You can say KMnO4, it converts SO2 in acidic medium to SO4 di negative and itself gets converted to Mn di positive, and with this you'll be getting the water molecules as well. Yes. Yes. Yes guys. Yes. Let me know in the chat box if you got it so that I can move on and talk about few more reactions right here which are very important. Let me know in the chat box fast. Let me know in the chat box fast if you got it. Hit the chat box guys with the thumbs ups. Yes. Hit the chat box with the thumbs ups. Fast. Wonderful guys, great. Yes. Okay, now guys understand. Talking about the K2Cr2O7, let me tell you, K2Cr2O7 is going to show the same reactions. See how, wait, see how guys. Only thing which I want you guys to remember, your K2Cr2O7, or you can write as Cr2O7 di negative, it gets converted to Cr plus 3 in acidic medium. Only thing you need to remember. In acidic medium, Cr2O7 di negative or K2Cr2O7, in acidic medium, it gets converted to Cr plus 3, right? Yes. Now guys understand. See, the same reactions which KMnO4 was showing, same reaction this will show. First thing, I'll say this K2Cr2O7 or Cr2O7 di negative, it converts Fe di positive to Fe tri positive only. Remember this. It converts oxalate ion C2O4 di negative to carbon dioxide. Yes, it converts I negative to I2. Only thing you need to remember. Yes, it converts Sn plus 2 to Sn plus 4. Yes, only thing you need to remember. And it converts what? It converts SO2 to SO4 di negative. Yes, and at the same time it converts H2O2 to O2. Yes, H2O2 to O2. Now I can write everything. I can write every damn reaction right here. I can write it. I can simply say your Cr2O7 di negative, it converts what? It converts H2O2. It converts H2O2 in which medium? In acidic medium. To what? To O2, and itself gets converted to Cr plus 3. With this add some water as well. The complete reaction done and dusted. Yes, same Cr2O7 di negative, it converts Fe di positive in which medium? In acidic medium. To what? It converts it to Fe tri positive and itself gets converted to Cr plus 3 and add some water molecules. Yes, the reaction is done. Similarly, the same Cr2O7 di negative, it converts oxalate ion C2O4 di negative in which medium? In acidic medium. To what? To carbon dioxide, and itself gets converted to Cr plus 3 and add some water molecules as well. Done. Reaction is done. Yes. Yes. At the same time guys, the same Cr2O7 di negative, it converts Sn plus 2 in which medium? In acidic medium. To what? To Sn plus 4. With this it gets converted to Cr plus 3 and add some water molecules as well. Done and dusted. Yeah. And at the same time, it converts SO2 to SO4 di negative. You can easily write that reaction as well. Or I negative reaction is there. Yes, Cr2O7 di negative, it converts I negative in acidic medium to what? To I2, and itself gets converted to Cr plus 3. And with this, add some water molecules as well. You can write every single reaction right here. You can write every single right here. You don't have to understand. You don't have to remember these reactions. Just remember one thing: Fe di positive gets converted to Fe tri positive. All these things you have to remember. That's it. You are done. Your job is done and dusted. Yeah. Yes. Let me know in the chat box if it is clear to every single guy so that I can move on to one more interesting thing right here. Yes, Angela, these reactions are in D block actually, okay? But I have summed up all these reactions of KMnO4 and K2Cr2O7 over here in Redox, yeah? Yes? Let me know in the chat box if everything is clear to you. Yes? Okay. So guys, let's move on. This is reaction which I told you just now, yeah? This is the reaction which I showed you right now. This is one more reaction which I showed you. This is one more reaction, 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 and dusted, yeah? Okay, now guys, now, understand. There are some substances which can act as the oxidizing agent as well, which can act as the reducing agent as well. Yes, there are some substances which can act both oxidizing agents sometimes and reducing agents sometimes. Yes. There are some substances which can act oxidizing as well as reducing agent over here, and H2O2 hydrogen peroxide is one among them. Hydrogen peroxide is one among them, and when the hydrogen peroxide acts as the oxidizing agent, H2O2 at that time gets converted to H2O. And how do I identify that? Understand. What about the oxidation state of oxygen right here in peroxide? -1. What about over here? -2. So -1 to -2. Oxidation state is decreasing. Decrease in oxidation state is what we call as reduction. If it is undergoing reduction, that means it is acting as the oxidizing agent. So H2O2 right here is acting as the oxidizing agent, and I want you guys to calculate the N factor of H2O2 right here. You can simply calculate it. I can say this is the initial oxidation state, this is the final oxidation state. Just calculate the change in the oxidation state. I can say final oxidation state, which is -2, minus initial oxidation state, which is -1. The value is going to come as 1, but this one is the change in the oxidation state for one oxygen atom, but I have two oxygen atoms, so I'm multiplying it by 2. The value is going to come as 2. So 2 is the N factor of H2O2 when it acts as the oxidizing agent right here. Yes. And when it acts as a reducing agent, it gets converted to O2. Again, this is -1, this is 0, -1 to 0. Increase in oxidation state. Increase in oxidation state is what we call as oxidation, and any substance which undergoes oxidation, that's what we call as reducing agent. So right here, H2O2 will be acting as the reducing agent. So people, if I want you guys to calculate its N factor, you can easily calculate it. Magnitude of final oxidation state of oxygen, which is 0, initial oxidation state, which is -1, change is going to come as 1. So 1 is the change in the oxidation state for one atom of oxygen, but I have two atoms, multiplying it by 2. So 2 is the N factor of H2O2 right here in this reaction. So people, remember, whenever H2O2 acts as the oxidizing agent or the reducing agent, its N factor in both the cases will be 2. Yes, there is one more compound. There is one more compound which can act as the oxidizing or the reducing agent, or just wait for that. Just you need to wait for that. Okay. So people, one question which is on your screen. I want you guys to calculate the N factor of I2 right here. You can do that. Calculate the N factor of I2. Very simple. The oxidation state of iodine is 0. The oxidation state of iodine right here is +5. You can calculate it, right? Now guys, oxidation state is changing from 0 to +5. This is the initial oxidation state. This is the final oxidation state. Calculate the change in the oxidation state. Change in oxidation state is going to be final oxidation state minus initial. The value is going to be as 5. But 5 is the change in the oxidation state for one atom of iodine. But I have two atoms, so 5 multiplied by 2 is 10. So N factor of I2 in this reaction is 10. Done and dusted. Yeah. Yes. Again guys, again, one more. Calculate the N factor of N2H4 right here. You can do that. The oxidation state of nitrogen right here will be -2. Yes, the oxidation state of nitrogen right here will be +3. So -2 to +3. This is the final oxidation state. This is the initial oxidation state. I need to calculate N factor of this substance right here. So I can simply say N factor of N2H4 right here is going to be final oxidation state, which is +3, minus initial oxidation state, which is -2. The value is going to come as 5. But 5 is the change in the oxidation state for one atom of nitrogen, but I have two atoms. So 5 multiplied by 2 is 10. So N factor of N2H4 right here is 10. Yes. Absolutely guys, absolutely. Moving on to one more reaction. IO4 negative change to I2. IO4 negative change to I2. What is the oxidation state of iodine right here? It's going to be +7. What about the oxidation state of iodine right here? It's going to be 0. +7 7 to 0. What about the change in the oxidation state? I can simply say this is the initial oxidation state of iodine, this is the final oxidation state of iodine. I need to calculate n factor of this IO4 negative. I'll be simply calculating change in the oxidation state of iodine, final, which is 0, minus initial, which is plus 7. The n factor is going to be 7. So 7 is the n factor of IO4 negative right here. Yes. Again, guys, I want you guys to calculate the n factor of this VO right here. What about the oxidation state of V right here? It's going to be plus 2. What about the oxidation state of V right here? How much is going to be? 5 2s are 10. 10 divided by 2 is 5. So it's going to be plus 5. So plus 2 to plus 3. What about the change? Change in the oxidation state of V right here, which is going to be final oxidation state minus initial oxidation state. Value is going to come as 3. 3 is the n factor of this VO right here. Yes. Absolutely, guys. You guys are perfectly doing it. You guys are perfectly doing it. Yes. Now comes one special case. I want you guys to give it a try properly and let me know its answer. I want you guys to give it a try properly and let me know the answer first. Let me know the answer first. Understand, guys, understand. Calculate the n factor, calculate the equivalent mass, calculate the n factor equivalent mass of Fe 0.940 right here. How will I be approaching to this sort of equation right here? Understand, guys. Let's assume the oxidation state of iron as X, okay? And how many iron atoms do we have? 0.94. I'm multiplying it by 0.94. Yes, plus what about the oxidation state of oxygen right here? It is minus 2. What about the net charge present on the molecule? It is 0. So X value will be 2 divided by 0.94, which is going to be 200 divided by 94. So people, this is the oxidation state of iron right here. Plus 200 divided by 94 is the oxidation state of iron right here. This is the average oxidation state of nitrogen right here. Sorry, iron right here. Now guys, understand. What about the oxidation state of iron right here in this compound? Can I say it's going to be plus 3? Yes. Now the oxidation state of iron is changing from this to this. Can I say this is the initial oxidation state of iron? Can I say this is the final oxidation state of iron? I'll be simply calculating change in the oxidation state. That is going to give me the n factor. Yes, calculate the change in oxidation state, which is going to be final oxidation state plus 3 minus initial oxidation state 200 by 94. 200 divided by 94. This is going to give me the change in the oxidation state of iron. But people, this is the change in the oxidation state of iron. This is the change in the oxidation state for one atom of iron. But do I have one atom or 0.94? I have 0.94 multiplied by 0.94 at the same time. Whatever value you are getting, that's going to give the n factor of it. And the value which you will be getting right here is going to be 0.82. Yes, so 0.82 around will be the value. Just a second. So 0.2. Just calculate this value. It's going to be 0.82. So I can say 0.82 is the n factor of this compound right here. Remember, n factor can be fractional as well. You can simply divide its molar mass by its respect to n factor. You'll be getting the equivalent mass of it. Let me know in the chat box if you got the concept properly or not. Absolutely, guys, you're perfectly saying it. Yes, yes, absolutely. Yes. Wonderful. Wonderful, guys. Wonderful. Okay. Now guys, till now we talked about those oxidizing agents and reducing agents in which oxidation state of only one element was changing. Yes, till now we talked about only those oxidizing and reducing agents for which the oxidation state of only one element was changing. Now we are going to talk about those oxidizing and reducing agents. We are going to talk about those compounds in which simultaneously oxidation state of more than one element changes. Yeah, yes. Now guys, understand what I'll say. Understand what I'll say. Till now I talked about only those compounds in which the oxidation state of only one element was changing. Now I'm going to talk about those compounds in which oxidation state of more than one element changes. For example, I'm taking one general compound like this, okay? Let's say this is my general compound, okay? Now people, if I'm assuming the oxidation state of both A and B is changing, what are going to be the possibilities? I can say oxidation state of A and B simultaneously can increase. Yes, oxidation state of A and B simultaneously can decrease. Oxidation state of A can increase, oxidation state of B can decrease. These are the three possibilities which we have right here. Yes. Now people, I'm going to talk about first two possibilities right now. I'm going to talk about the calculation of the N factor of that substance in which oxidation state of more than one element simultaneously either increases or decreases. I'm going to talk about those compounds in which oxidation state of more than one element simultaneously increases or decreases. How do we calculate their N factors? There is one simple trick. Understand. See, in order to calculate the N factor of the substance in which oxidation state of more than one element increases or decreases at a time, we calculate their N factor by the formula mod of N1 plus N2. Yes, very simple. Okay. Now guys, say, what is the oxidation state of iron right here? I'll say plus 2. What is the oxidation state of carbon right here? I'll say plus 3. What is the oxidation state of iron right here? Plus 3. What about the oxidation state of carbon right here? It's plus 4. Can I say the oxidation state of iron is changing from plus 2 to plus 3? So the oxidation state of iron is increasing. Yes, oxidation state of iron is increasing. What about the oxidation state of carbon? Is the oxidation state of carbon also increasing from plus 3 to plus 4? Absolutely, oxidation state of carbon is also increasing from plus 3 to plus 4. Can I say this is the compound in which oxidation state of more than one element is increasing simultaneously? How do I calculate its N factor? N1 plus N2. Very simple thing. Understand guys, plus 2 to plus 3. What is the change in the oxidation state? Final minus initial. Yes, so N1 value I got to be 1. Final minus initial, that is 1. What about the change in the oxidation state of carbon? It is going to be final plus 4 minus initial plus 3. Change will be 1. 1 is the change for one atom of carbon, but I have 2 atoms, so N2 value is going to be 2. People, I got the value of N1, I got the value of N2. I just have to add them up, so it's going to be 1 plus 2, it's going to be 3. So N factor of this ferrous oxalate right here is going to be 3. If you got its N factor, you can easily calculate its equivalent mass. How? Molar mass of this compound by its respective N factor. Yes, got it. How to do these sort of questions? Yes, let me know in the chat box. Let me know in the chat box if you got it. Yes, wonderful guys, great job. Yes, let me give you a few more examples by means of which we can get to know the concepts properly. See guys, what about the oxidation state of AS and sulfur right here? Just do the crisscross thing which you would have studied in your class 8th as well. Class 8th mein pada hoga. Crisscross kar lo yahan pe. So it's going to be plus 3. It's going to be minus 2. Yes. What about the charge on this AS right here? It's going to be plus 5. What about the charge on this sulfur right here? Plus 6. Okay. So oxidation state of AS is changing from plus 3 to plus 5. Can I say the oxidation state of AS is increasing? Yes. What about the oxidation state of sulfur? It is also increasing. It is also increasing from minus 2 to plus 6. Now, this is the compound in which oxidation state of more than one element is increasing. How do I calculate its N factor? Can I say it's simply going to be mod of N1 plus N2, which I've shown you a few minutes back? Yes. Now guys, I need to calculate the value of N1. I need to calculate the value of N2. Once I get to know the value of N1 and N2, I can simply add them up. I'll be getting the N factor overall. Yes, very simple. Now guys, understand. See, from plus 3 to plus 5, what is the change? From plus 3 to plus 5, I can say N1 will be simply equal. From plus 3 to plus 5, this is the final oxidation state, this is the initial oxidation state. Final is plus 5 minus initial is plus 3. Can I say the value is going to come as 2? So 2 is the change in the oxidation state for one AS atom, but I have 2. I'm going to multiply it by 2. So N1 value is 4. N1 value I got to know as 4. Now people, what about the N2 value? What about the N2 value? Again, you can calculate it. Minus 2 to plus 6. Minus 2 to plus 6. Calculate the change. Final oxidation state, initial oxidation state. Final is plus 6. Final is plus 6 minus initial is minus 2. The value is going to come as 8. 8 is the change in the oxidation state for one sulfur, but I have 3 sulfurs, so multiplied by 3. 8 3s are 24. I got the value of N2 right here, which is 24. I got the N1 value, I got the N2 value, so N1 plus N2 is going to be 28. So the N factor of this compound right here is going to be 28. If you got its N factor, you can divide its molar mass by its respect to N factor. You can get the equivalent mass. Yes. Let's get to know one more. Understand properly what I'll say. Understand properly what I'll say. First of all, let's do the crisscross thing so that we can get to know the oxidation states. So people, oxidation state of copper is going to be +1, it is going to be -2. Yes. What about the oxidation state of copper? Right here, +2. What about the oxidation state of sulfur? Right here, +4. Yes. Now people, understand, copper shows its oxidation state. Copper changes its oxidation state from +1 to +2. There is increase in the oxidation state of copper. Sulfur is changing its oxidation state from -2 to +4. There is again increase in the oxidation state of sulfur. So people, this is again the compound in which the oxidation state of more than one element increases. Yes. And we know how do we calculate the n factor of the substance in which the oxidation state of more than one element increases or decreases simultaneously. We can simply calculate it. Yes, you know the formula. I've told you that it's going to be mod of n1 plus n2. Yes. Absolutely. Now, I need to know the value of N1. I need to know the value of N2. So let's get to know the value of N1 and N2 respectively right here. See guys, N1, change in the oxidation state of copper, +1 to +2. This is final oxidation state. This is initial. Final minus initial. So final is +2 minus initial is +1. The change is going to be 1. 1 is the change in the oxidation state for one atom of copper, but I have 2. I'm multiplying it by 2. The value is going to come as 2. So I got the N1 value simply as 2. Yes. Again, what about the N2 value, guys? -2 to +4. -2 to +4. This is the final oxidation state. This is the initial. Just do the subtraction. Final oxidation state minus initial oxidation state. The value is going to come as 6. So 6 is the change in the oxidation state for one atom of sulfur, and I have only one atom. So N2 value is simply 6. I got N1. I got N2. I can calculate the overall n factor of this compound. It's going to be 6 plus 2. That means 8. Okay. So 8 is the n factor of this compound right here. Yes. Very simple. Okay, now let me see if there is more examples or not. Okay, we have got one more example. You can kill it out. Yes. So people, just do the crisscross thing. Over here, oxidation state of Bi is +3. Over here, oxidation state of sulfur is -2. What about the oxidation state of Bi right here? It's going to be +2, +5. What about the oxidation state of sulfur right here? It's going to be 0. Is the oxidation state of Bi increasing or decreasing? Oxidation state of Bi is increasing. Is the oxidation state of sulfur increasing or decreasing? Oxidation state of sulfur is also increasing, -2 to 0. So I'll say this is again the compound in which oxidation state of more than one element is increasing simultaneously. And how do we calculate its n factor? It's going to be mod of n1 plus n2. So I need to calculate n1 value. I need to calculate n2 value first. This is n1 for example. This is n2 for example. Yes. So people, let's get to know the value of n1 and n2 respectively right here. n1 is going to be change in the oxidation state of Bi, which is final oxidation state, minus initial oxidation state, which is +3. The value is going to come as 2. So 2 is the change in the oxidation state for one Bi atom. I'm going to multiply it by 2. Why? Because I've got 2 Bi atoms. The value is going to come as 4. So N1 value is simply 4. What about the N2 value? -2 to 0. Just calculate N2. Change in the oxidation state. Final minus initial. Final is 0. Initial is -2. So 0 minus -2. Value is going to come as 2. So 2 is the change in the oxidation state for one atom of sulfur. But I have 3 atoms. I'm multiplying by 3. 2 multiplied by 3 is 6. So N2 value I got to know as 6. And this is the compound in which oxidation state of both the elements is increasing simultaneously. And how do we calculate its n factor? N1 plus N2. So 6 plus 4, that means 10. So n factor of this substance is 10. So you got to know its n factor. You can calculate easily its equivalent mass. Just divide its molar mass by the 10. You'll be getting the equivalent mass of this substance right here. Yes. How much more time? I'll take around 15-20 minutes more. Just wait guys, just wait. 15-20 minutes more we'll finish the n factor completely. Then in the next session, which is going to be part 2 of the redox, in that we'll be finishing the titrations. Yes. Yes. Right. Let's move on. One more substance, guys. One more substance. But this is one more case. Till now, we were talking about that compound in which oxidation state of more than one element either increases or decreases simultaneously. Yeah. Now I'm going to talk about that compound in which oxidation state of one element increases and other element decreases simultaneously. Yes. I'm going to talk about that compound in which oxidation state of one element increases and another element decreases simultaneously. How do we calculate their n factors? Again, I'm going to make you understand by means of formula. N factor of this sort of a compound is mod of n1 minus n2. Yes, yes, very simple. Understand, guys? Now how do we approach these sort of questions? Understand. First of all, do the crisscross thing. It's going to be +3, it's going to be -2. Yes, we got the charges. It is going to be +2, it is going to be -2, it is going to be +4. Yes. Is the oxidation state of iron increasing or decreasing? Oxidation state of iron is decreasing. Is the oxidation state of sulfur increasing or decreasing? Oxidation state of sulfur is increasing. Yes. So I can say this is the compound in which oxidation state of one element is decreasing, oxidation state of another element is increasing. How do I calculate its n factor? N1 minus N2. Dusted. Yes. I just need to calculate the N1 value. I just need to calculate the N2 value. We are done with it. Yes. Yes, understand, guys. So first of all, let's get to know the value of N1. Let's get to know the value of N2. So first of all, +3 to +2, change in the oxidation state. N1 value is going to be final oxidation state of iron minus initial oxidation state of iron. Final is +2 minus initial is +3. The value is going to be 1. 1 is the change in the oxidation state for one iron atom. But I have two iron atoms. I'm multiplying it by 2. So I got the N1 value. Similarly, guys, I'll be getting the N2 value as well. Final minus initial. Final is +4. Initial is -2. So final minus initial, the value is going to be 6. The 6 is the change in the oxidation state for one sulfur. I have 3 sulfur atoms, so 6 multiplied by 3 is 18. So I got the N1, I got the N2. I can simply take the mod of them. Mod of N1 minus N2 is going to come as 16. So 16 is the n factor of this compound right here. If you know its n factor, just divide its molar mass by its n factor. You'll be getting its equivalent mass. Yes, absolutely. Yes, Nirbhay, you can come to my long-term sessions on Vedantu. Yes. Okay, let's talk about one more case. People, do you remember I gave you the structure of BASC and whole twice? Do you remember that? I gave you the structure of BASC and whole twice. If you remember, yes. I gave you the structure of BASC and whole twice in the beginning, if you remember, yeah? Do you remember? The structure of BASC and whole twice, if you remember, it was something like this. Yes, if you remember. Yes, nitrogen was in -3 oxygen state, carbon was in +4 oxygen state, sulfur was in -2 oxygen state, barium was in +2 oxygen state. We talked about this in detail. Yes, we talked about this in detail in the beginning of the session. Yeah, now guys understand. Ba, its oxygen state right here is +2, right? Sulfur, its oxygen state right here is -2. Carbon, its oxygen state right here is +4. What about the oxygen state of nitrogen? Oxygen state of nitrogen is -3, correct? What about the oxygen state of sulfur right here? It's going to be +6 when you will calculate it. What about the oxygen state of barium right here? +2. What about the oxygen state of oxygen? It's going to be minus. Yes, HCN, Hc triple bond N. Nitrogen is more electronegative, so all the 3 electron pairs will be shifted towards nitrogen. So nitrogen will have -3, carbon will have +3. What about this single bond? Carbon is more electronegative, so -1, +1. What about the charge on this carbon overall? It's going to be +2. So +2 is the oxidation state of carbon right here, and -3 is the oxidation state of nitrogen right here. Now we will understand which all elements are showing the change in the oxidation state. I can say oxidation state of sulfur is changing from -2 to +6. So oxidation state of sulfur is increasing. Yes, but what about the oxidation state of nitrogen? Oxidation state of nitrogen is remaining same on both the sides, yeah? But oxidation state of carbon is changing. Oxidation state of carbon is changing from +4 to +2. Yes. Now people, understand. Is the oxidation state of carbon increasing or decreasing? Oxidation state of carbon is decreasing from +4 to +2. Yes. So I can say this is the compound in which oxidation state of one element increases, another one decreases. How do I calculate its n factor? Its n factor is going to be simply mod of N1 minus N2. Yes, very simple. Now guys, I need to get the value of N1. I need to get the value of N2. Once I get the value of N1 and N2, I'm done. Yes. Now, N1 value, N1 value. N1, for example, is the change in the oxidation state of sulfur. N1 will be simply equal change in the oxidation state of sulfur, which is final oxidation state of sulfur minus initial oxidation state of sulfur, which is -2. Yes, the value is going to come as 8, and 8 is the change in the oxidation state for one sulfur atom, but I have two sulfur atoms, so 8 multiplied by 2 is 16. I got the value of N1, which is 16. Yeah. Now, what about N2 value? What about N2 value? Carbon is changing its oxidation state from +4 to +2. N2 value will be equal to mod of change in the oxidation state of carbon, which is going to be final oxidation state of carbon minus initial oxidation state of carbon, which is +4. The value is going to come as 2. 2 is the change in the oxidation state for one atom of carbon, but I have two atoms, so I'm multiplying it by 2. The value is going to come as 4. I got the N1 value, I got the N2 value. Once you get the N1 and 2, you can get the overall N factor as 16 minus 4, it's going to be 12. So 12 is the N factor of this substance. So you got the N factor of this substance. You can calculate its equivalent mass by dividing the molar mass of the substance by its respective N factor. Yeah? Yes? Yes? Okay, let's move on. People, this is the last case of the today's session, okay? This is the last case of the today's session, okay? How to enroll to my batch in the Vedantu platform? Yashwini, you can go to the starting of the video, okay? In the starting of the video, I have given you some links, okay? Or there's a link in the description box of the video as well. Click on that link, get the particular course whatsoever you want to get in, okay? Use the coupon code which I have given you, which is mentioned there in the description box of the video. You can get the discounts as well. You can get enrolled in my batch, yeah? All right, now people, one more important case which we are going to dust now. Yes? Yes? Now understand, guys. Let's say I've got a reaction like this. Understand, A2, let's say it gets converted to A positive plus A negative. Yes? Let's assume this A right here is present in its standard state. If it is present in its standard state, its oxidation state is going to be 0. What about the charge on this A right here? Can I say it's +1? What about the charge on this A right here? Can I say it's going to be -1? Is the oxidation state of A increasing or decreasing? It's increasing. Is the oxidation state of A increasing or decreasing? It's decreasing. Increase in the oxidation state is what we call as oxidation. Decrease in the oxidation state is what we call as reduction. Can I say some part of A2 is undergoing oxidation, some part of A2 is undergoing reduction? If some part of A2 is undergoing oxidation and its rest of the part is undergoing reduction, so I must say A2 is undergoing disproportionation. Yes, I must say A2 is undergoing disproportionation. Any substance in which some part of it undergoes oxidation whereas the rest part undergoes reduction, we say that substance undergoes disproportionation. And how do we calculate the N factor of such kind of a substance? How do I calculate N factor of such kind of substance? It's going to be very simple. You will get the value of N1, you will get the value of N2, just get the value of N1 and N2. Its N factor is simply going to be N1 multiplied by N2 divided by N1 plus N2. Yes? Simple trick by means of which you can calculate its N factor, right? This is particularly for NEET. This is not for boards. This is for NEET, particularly, yeah? Now guys, understand. See, First of all, Br2 we have. Let's say this is right now in its standard state, its oxidation state is 0. What about the oxidation state of Br right here? It is going to be, you can calculate it, +5. Yeah. What about the oxidation state of Br right here? It's going to be -1. Correct? Correct? Now guys, understand. Oxidation state of Br is changing from 0 to +5. So that is increase in the oxidation state of Br. Now similarly, oxidation state of Br is changing from 0 to -1. That means oxidation state of Br is decreasing. Right? Can I say some part of Br is undergoing oxidation, some part of Br2 right here is undergoing reduction? Can I say Br2 right here is undergoing disproportionation? Right? It is undergoing disproportionation. If it is undergoing disproportionation, how do I calculate its N factor? Its N factor is going to be N1 multiplied by N2 divided by N1 plus N2. Yes, I need to get the value of N1. I need to get the value of N2. We are done, right? Get the value of N1, guys. N1 will be final oxidation state, which is plus 5, minus initial oxidation state, which is 0. It is going to come as 5. 5 is the change in the oxidation state for one atom of Br, but I have two atoms. I'm multiplying it by 2. The value is going to come as 10. Now, similarly, get the value of N2. It's going to be 0 to minus 1. So, minus 1 is the final, minus initial is the 0, value is going to come as 1. 1 is the change for one atom, but I have two atoms. I'm multiplying it by 2, so the value is going to come as 2. I got the value of N1, I got the value of N2. You can simply use it in the relation. It's going to be 10 multiplied by 2 divided by 10 plus 2. The value is going to be 20 divided by 12. 20 divided by 12 means 4, 5, 4, 3. 5 by 3 is the n factor of this Br2 right here. If you got its n factor, you can calculate its equivalent mass. Yes, molar mass by its n factor. Yes. Zulfi, no. N factor cannot be negative, bro. Yes? Okay, let me give you one more example, guys. Let me give you one more example. Understand properly. The oxidation state of phosphorus right here is 0. The oxidation state of phosphorus right here is minus 3. The oxidation state of phosphorus right here, it's going to be plus 1. Right? It's going to be plus 1, right? It's going to be plus 1, understand. So the oxidation state of phosphorus is changing from 0 to minus 3, that means decrease in oxidation state. Oxidation state of phosphorus right here is increasing from 0 to plus 1, that means increase in oxidation state, correct? So can I say this P4 is undergoing disproportionation right here? So its n factor is going to be N1, N2 divided by N1 plus N2. Calculate the value of N1, calculate the value of N2, you are done. Yes, I can say N1 value is going to be change in the oxidation state, which is going to be final minus initial. The value is going to be 3. 3 is the change in the oxidation state for one atom of phosphorus. I have 4 atoms, 3 4s are 12. So 12 is the n factor of this P4 right here. Similarly, I can get the value of N2 from 0 to plus 1. So final oxidation state is plus 1 minus initial oxidation state is 0. The value is going to come as 1. 1 is the change in the oxidation state for one atom of phosphorus, but I have 4 atoms, so 1 multiplied by 4 is 4. I got the value of N1, I got the value of N2. I can simply multiply the 2 and add the 2. I can say n factor of overall is going to be 12 multiplied by 4 divided by 12 plus 4. The value is going to come as 3. So 3 is the n factor of P4 right here. If you got the n factor of P4, you can easily calculate its equivalent mass. Yes, molar mass divided by n factor. Yeah. Yes. Yes. Yogesh, without balancing the reaction, I'm showing you this. Okay, these are all the tricks. Without balancing the reaction, you're not supposed to balance the reaction. You can easily calculate it. Yeah, like this. Yes. Wonderful. Just remember all these. Yes. Now, guys, okay, this is something which we are going to discuss in the next session, correct? But before this, I need to tell you one more thing. People, I'm giving you one thing as the homework. I'm writing a reaction H2O2, it gets converted to H2O plus O2. Let me know the equivalent mass of this H2O2 in the chat box once the session ends, okay? Tonight only, after the session, let me know the equivalent mass of H2O2 in this reaction, okay? This is your homework. Correct? So people, our first part of redox is done. We are done with the 65% or 75% of the redox, okay? We are left with 30% of it, which includes your equivalent concept, which involves the redox titrations, acid-base titrations, volume strength, and a lot of questions. I'm going to come up with that session soon, and you'll be getting the notification for that once you hit the bell icon and subscribe the channel. Yes, you are going to get the notification of that soon. Yeah. Yes. So people, I'll be starting the organic also, guys. Just wait for it. Let me finish off everything. I'll be finishing everything. Wait. You just have to wait. I'll start your whole. I'll finish your whole syllabus before your NEET 2021. Trust me on that. Yeah. The aims. I didn't get you, bro. Yes, Arun. Yesterday I cancelled the session because there were some connectivity issues. That's why I cancelled the session. Yeah. So people, let's take a leave now. I think this is enough for today. I think we are live from past 2.5 hours. Yeah, is that? Yes? Okay, so people, with this we are done with the first part of the Redox. I'll meet you tomorrow at the same time, okay? Or maybe tomorrow I cannot meet you guys because tomorrow I've got some work, okay? So I'm really sorry for that. Tomorrow I'll be on leave on this channel, okay? Day after tomorrow, I'll see you again with something called as solid state, if you remember. Yes? Yes? So people, till then, you guys take care. By the way, one more thing. Tomorrow at 9 p.m., I'm going to take one short series from the chapter mole concept on a different channel, which is going to be VJE Enthuse. Let me write the channel name, VJE Enthuse. This is one more channel, guys, in which I take chemistry. VJE Enthuse, and this channel is particularly for JE people. But let me tell you, tomorrow at 9 p.m. or maybe 8:30 p.m. I'm starting one more marathon session, one short session from the chapter mole concept. Yes, you can watch that session as well. Tomorrow 8:30 on the channel VJE Enthuse. You can watch that. As well. So see you guys tomorrow at 8:30 on VJE Enthuse. Till then, you guys take care. Bye-bye. God bless you all. Love you all. Take care, guys. Bye-bye.